How do factories churn out Krispy Kreme donuts, Snickers, and Lay's at full speed without the texture falling apart? One wrong proof or one overfried chip can turn perfect into trash in seconds. In this documentary, we go behind the scenes from dough to fryers, uncovering the secret methods these brands use to make their products that they don't want you to know. The defining feature of a Krispy Kreme style ring donut is the thin, tender crust and airy interior that come from a dough that is proofed to a narrow endpoint, fried with a controlled flip, then glazed while the surface is still warm enough to accept a uniform film without soaking. Everything is organized around the proof to fry handoff, so the line is built to keep dough pieces moving continuously from cutting to proofing to oil without waiting. The dough system starts with flour and liquid staged to produce a consistent final dough temperature. Flour is sieved to remove lumps and to stabilize flow into the mixer. Sugar is screened so crystal size does not vary significantly because sugar affects both fermentation rate and browning. Salt is weighed precisely to control dough strength and yeast activity. Yeast is prepared as a dry addition or slurry, so it disperses evenly. Fat is tempered so it blends smoothly without streaking. Water and dairy liquids are tempered because final dough temperature is one of the strongest predictors of proof time. Mixing builds a gluten network that can expand without tearing. The mixer begins at low speed to hydrate flour and incorporate yeast and sugar uniformly, then increases speed to develop gluten to a target elasticity. The target is not maximum strength. The dough must be strong enough to hold gas during proofing and frying, but extensible enough to sheet cleanly and cut without shrink. Fat is introduced after initial gluten development, so it softens the network rather than blocking formation. The mix endpoint is judged by dough smoothness and elasticity and by temperature. If the dough exits too warm, it will ferment too fast and become sticky on rollers. If too cool, it will be tight and resist expansion. After mixing, the dough enters a short rest to equalize moisture and relax gluten. Relaxation reduces snapback in sheeting, which is essential for ring accuracy. During this rest, early fermentation begins creating small gas cells. The rest is timed so the dough remains workable and does not overexpand before forming. Forming begins with sheeting. The dough passes through a series of reduction rollers that gradually decrease thickness. Large reductions are avoided because they create stress lines that show up as weak spots during frying. Gauge rollers at the end set the final sheet thickness, and that thickness becomes a primary determinant of donut weight and final crumb thickness. The sheet then enters rotary cutting, where an outer ring and an inner hole are cut in one motion. Cutter sharpness is critical because dull cutters compress the edges and create ragged rims that absorb more oil and brown unevenly. Scrap dough around the cutouts is lifted and recycled at controlled ratios because heavy recycling increases work input and changes dough strength. Cut rings are transferred onto proofing screens or belts with minimal distortion. Transfer height is kept low, and the dough is supported so it does not stretch. Stretching changes ring thickness and causes uneven expansion. The rings then enter the proofer, which is essentially a controlled fermentation chamber that raises the dough to near final volume. Proofing conditions are set to achieve rapid, even expansion without forming a surface skin. Temperature controls yeast activity. Humidity prevents the surface from drying and sealing, which would trap expanding gas and cause blisters. Proof time is tuned so the ring becomes light and inflated, yet still strong enough to be moved and flipped in oil. Underproof produces dense donuts with thicker crust and less lift. Overproof produces fragile rings that collapse when they hit the fryer or when they are turned. The fryer is designed to set the structure quickly while preserving a thin crust. Oil temperature is held in a narrow band and monitored continuously. When proofed rings enter the oil, surface water flashes to steam, creating outward pressure that expands the ring further and helps delay oil penetration in the earliest seconds. Starch gelatinizes at the surface and forms the initial crust. Proteins coagulate and lock structure. As the surface dries, browning begins and color develops. Rings typically fry one side first while floating. Conveyor speed sets the dwell on the first side, then a turning mechanism flips the ring. Flip timing is a major control because the first side must be set enough to support the ring during rotation, but not so overcooked that it becomes thick and dark. After the flip, the second side fry completes structure set and balances moisture loss. The total fry time is tuned to yield a pale, thin crust that remains tender rather than thick and crunchy. Oil management is continuous because crumbs and fragments break off and burn, darkening oil and changing heat transfer. Filtration removes fines. Oil circulation maintains uniform temperature across the fryer width. Fresh oil addition and controlled bleed maintain quality, so color remains consistent from hour to hour. Stable oil behavior is essential because even small changes in heat transfer shift crust thickness and glaze pickup. As rings leave the fryer, surface oil drains immediately. Drain belts and brief vibration shake off free oil. Removing surface oil matters because it affects glaze adhesion and prevents greasy patches that repel glaze. The donuts then move onto a short cooling conveyor, but the cooling is not intended to fully cool them. It is intended to bring the surface into the glaze window. Glaze is applied while the donut is still warm. The glaze is a sugar solution or suspension mixed to a defined solids level. Solids level determines film thickness and set speed. The glaze is held warm enough to flow smoothly, but not so hot that it becomes too thin. Donuts enter a glaze waterfall or curtain where glaze coats the surface. Excess glaze drains as donuts travel on a belt. The warm donut surface helps the glaze spread evenly and then set. If donuts are too hot, glaze becomes excessively thin and runs off, leaving a patchy coat. If too cool, glaze sets too quickly and creates uneven coverage and a grainy texture. After glazing, the donuts move through a setting zone where glaze crystallizes. Airflow here is controlled because strong airflow can dry glaze too fast and create a rough finish, while weak airflow can leave glaze tacky and prone to sticking in cartons. The objective is a smooth, thin glaze shell that remains slightly delicate and glossy. For filled products, filling is typically done after the donut has cooled further and the crust has stabilized. A controlled injection system uses needles to place a measured dose of filling. Filling viscosity is tuned so it flows through needles without tearing the crumb and then holds shape without leaking. Needle depth and dose volume are controlled so filling is distributed without blowouts. If a cut and fill format is used, a slit is made and a nozzle deposits filling into the cavity, then the surface is finished and allowed to set. Chocolate icing or other coatings are applied after glazing or instead of glazing depending on format. These coatings are typically fat-based and set by cooling rather than crystallizing like sugar glaze. Coating temperature and viscosity determine thickness and surface smoothness. Toppings are applied while the coating is tacky so they adhere before the surface sets. Packaging and handling are built to protect the glazed surface, which can mark easily. Donuts are typically loaded into cartons that prevent stacking pressure on the glaze. Carton loading uses guides that minimize contact with the top surface. If the product is individually wrapped, the donuts must be fully set and cooled to avoid condensation inside the wrap and to avoid smearing. Wrap films are selected to manage moisture because donuts dry out quickly if exposed to air. Snickers manufacturing can be understood from the cutter backward because the entire line is built to deliver a layered slab that is firm enough to slice cleanly, stable enough to ride through a chocolate curtain, and uniform enough that every bar finishes at the same weight. At the cutter, the slab must present a flat top surface, a consistent total thickness, and a predictable resistance to the knife. If the slab is too soft, caramel smears and drags, nuts dislodge, and edges tear. If the slab is too hard, the caramel fractures and the nougat can crack into ragged faces that later create coating voids. The plant therefore shapes and cools each layer so the combined slab reaches a narrow cut window before portioning begins. The slab is built on a continuous belt. The bottom layer is aerated nougat. Nougat begins with two inputs that are prepared separately so they can be combined without collapsing the bubble structure. A cooked syrup that defines solids and elasticity, and a foam phase that carries metered air. Syrup cooking starts with sugar and glucose syrup streams that are metered into a cooker and concentrated. The cook endpoint sets the moisture level in the final nougat. A higher moisture syrup yields a softer nougat that can slump under the caramel layer. A lower moisture syrup yields a tighter nougat that becomes chewy and resists cutting. The cooker is operated to a precise endpoint, and the syrup is delivered forward at a controlled temperature so it strengthens foam but does not scorch it. The foam phase is produced from a protein solution. The solution is mixed to a defined concentration and fed to a continuous aerator. Air is metered in, and shear is applied to create small, uniform bubbles. Bubble size distribution matters because large bubbles collapse and create voids, while small bubbles create a smooth, light texture. Density is measured continuously because density is the direct control for nougat weight and bite. If density drifts, the finished bar weight drifts. Syrup and foam merge in a continuous mixer designed to fold rather than whip. Folding distributes syrup through foam without breaking bubbles. Syrup heat partially sets the protein films and locks the microcell structure. Fat is injected as a thin stream to soften bite and reduce stickiness. Emulsifiers can be added in small doses to stabilize the air-fat sugar system and improve flow at the depositor. The mixed nougat exits as a warm, aerated mass with controlled viscosity. Nougat is deposited onto the moving belt as a continuous slab. A spreader head lays down a wide band, and gauge rollers set thickness. Thickness control is critical because it defines the core height and influences later cooling time. The slab enters a cooling tunnel with staged zones. Early zones firm the surface enough to support caramel deposition. Later zones remove heat more gradually so the interior firms without forming a brittle skin. The target exit condition is a nougat slab that is firm but still receptive at the surface so caramel can bond. Caramel is prepared in a separate stream because it requires different cooking and different set behavior. Sugar and glucose syrup are cooked with dairy components to develop caramel notes and reach an elastic solids endpoint. The endpoint determines whether caramel behaves as a clean sheet or as a smear. Too low solids and caramel drags on knives. Too high solids and caramel fractures, especially when nuts create stress points. Fat is added to smooth the matrix and reduce tack. The caramel is cooled to a working temperature where viscosity is stable for deposition and held in jacketed tanks with gentle agitation to prevent skin formation. Peanuts are prepared as a topping stream that must spread evenly and remain dry. Roasted peanuts are screened to remove fines and broken pieces. Fines create dust and uneven coverage. Oversized pieces create peaks that cause thin chocolate spots later. The peanuts are cooled after roasting so they do not warm the caramel surface and change tack behavior. They are stored in dry conditions so they flow freely through spreaders. Layering begins when the nougat slab reaches the caramel station. Caramel is deposited as a continuous layer using a slot head. A leveling bar spreads it to uniform thickness. Temperature matching is essential. If caramel is too hot, it softens the nougat surface and creates a weak interface. If too cool, it does not fuse and can delaminate later. The line targets a condition where caramel wets the surface slightly and then begins to set as it moves forward. Immediately after caramel deposition, peanuts are applied. A spreader distributes nuts across the full width at a controlled mass flow. Distribution must be uniform, so every bar receives a similar nut density. A light pressing station can embed nuts slightly into caramel to improve mechanical lock. Pressing is controlled to avoid crushing nuts and to avoid squeezing caramel sideways, which would create thick edges and thin centers. After nut application, the slab enters a conditioning zone. This zone firms the caramel layer enough for cutting and locks nut position, so nuts do not slide when the slab is later accelerated. Cooling is staged to avoid differential contraction between nougat and caramel, because differential contraction can cause the slab to curl. Curling leads to uneven coating thickness and cutting errors. The slab is held flat by belt support and cooled to a target firmness. Edge trimming removes uneven edges where thickness variation is most common. Trim is collected for controlled rework streams. The main slab then enters lane cutting. Rotary knives slice the slab into long lanes of constant width. A crosscutter then slices lanes into bar lengths. Knife timing is synchronized to belt speed to maintain consistent weight. Knife surfaces are managed to reduce caramel buildup that would tear edges. Clean edges are important because ragged edges trap air under the chocolate curtain and cause voids. The cut bars are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges. Transfer points are designed with minimal drop height because impact can dislodge nuts and dent nougat. A brief pre-chill can be used to firm the surface and improve chocolate coverage. Pre-chill is balanced so the bars do not become so cold that condensation forms when they enter warmer chocolate equipment. Chocolate coating is prepared and held in a tempering loop. Chocolate is melted and filtered to remove unmelted fragments. Tempering creates a stable seed crystal population through controlled cooling and reheating. Working temperature is maintained tightly because viscosity defines curtain thickness and coat weight. Viscosity that drifts too high produces heavy coatings and thick feet. Viscosity that drifts too low produces thin coatings and exposed corners. Enrobing coats the bars with a top curtain and a bottoming system. The top curtain covers the top and sides. The bottoming system coats the underside, sealing the bar and protecting caramel from exposure. Excess chocolate drains through a wire belt. Air knives smooth the surface and control foot thickness. Air knife settings are tuned so they remove excess without exposing nut peaks at corners. If a top drizzle pattern is required, it is applied immediately after enrobing while the surface is still tacky. A stringer deposits thin lines that bond to the base coat. The bars then enter the cooling tunnel. Cooling is staged to set the chocolate and preserve surface quality. The first zone sets the surface quickly so the coating does not slump and nuts do not shift. Subsequent zones cool more gradually to promote stable cocoa butter crystals and reduce bloom risk. Tunnel humidity is controlled to prevent condensation that would cause sugar bloom and dullness. Bars exit the tunnel at a temperature suitable for wrapping with a coating hard enough to resist scuffing. After cooling, inspection checks coating coverage, shape, and weight. Vision systems detect exposed edges and coating voids. Weight checks confirm portion control across cutting and coating. Bars outside tolerance are diverted. Chocolate rework is remelted and returned upstream. Nougat and caramel rework is handled separately because their aeration and moisture differ from fresh streams. Wrapping begins once bars are fully set. Flow wrappers form film around each bar and seal it with controlled heat and dwell time. Film tension is controlled to avoid scuffing the coating. Coating is applied for traceability. Wrapped bars are collated into multi-packs or cartons, then case-packed. Lay's-style potato chips are manufactured by controlling three things more tightly than anything else: slice geometry, surface starch, and oil temperature. When those three are stable, the process reliably turns raw potatoes into thin, brittle chips that drain cleanly, accept seasoning evenly, and stay crisp inside a sealed bag. The line is easiest to follow from the seasoning drum backward because seasoning performance tells you whether the upstream steps produce the right surface. Chips that are too wet reject powder and clump. Chips that are too dry fracture into excessive fines. Chips that carry excess surface oil feel greasy and carry seasoning unevenly. The factory therefore builds chips so they exit the fryer with a narrow moisture and oil window before they ever reach flavor application. The final steps start at de-oiling. Chips exit the fryer on a mesh conveyor and immediately pass over vibrating drains. Vibration shakes off free oil while the chips are still hot and rigid enough to tolerate movement. Air knives or blowers can strip oil film from the surface and from curled edges. This is not a cosmetic step. Excess surface oil can cause seasoning to clump and can also migrate into the bag headspace, increasing the perception of greasiness. De-oiling settings are tuned so oil is removed without cracking the chips into fragments. From de-oiling, chips flow into a rotating seasoning drum. The drum provides gentle tumbling, so every chip surface is exposed. Seasoning is dosed as a fine powder or a blend and is metered by mass flow to match chip throughput. Adhesion relies on a thin oil film that remains on the chip surface. Too much film causes heavy seasoning pockets. Too little film yields bare chips. Drum speed and fill level are adjusted so chips roll rather than slide, because rolling distributes seasoning and minimizes breakage. A short dwell time allows seasoning to distribute fully without grinding chips into fines. Immediately after seasoning, chips move toward packaging, but they first pass through screening. Screens remove small fragments and fines produced by slicing and frying. Removing fines improves bag appearance and also prevents seals from being contaminated by dust. Fines also absorb more oil and can go stale faster, so their removal improves consistency. Packaging begins with portioning into bags using multi-head weighers. Chips are lightweight and irregular, so the weigher uses multiple small hoppers and selects combinations that hit target weight. Drop paths are designed to reduce breakage. Bags are formed from barrier film that resists oxygen and moisture transmission. Nitrogen flushing is commonly used to displace oxygen and to create headspace that cushions chips. The bag is sealed with heat and pressure. Seal parameters are tuned so seals hold without wrinkles that would leak. All of those downstream steps assume chips arrived with the correct structure, which is created in the fryer. Frying is not just cooking. It is a controlled dehydration process that forms a rigid, porous matrix. Chips enter hot oil and water at the surface flashes to steam. Steam leaves through the sliced surfaces, creating pores and crispness as moisture content drops. Oil temperature is held in a narrow band because it controls how fast water leaves and how much oil enters. If oil is too cool, chips stay in the fryer longer, absorb more oil, and remain flexible rather than crisp. If oil is too hot, the surface can brown before moisture leaves evenly, producing dark edges and fragile structure. Residence time in the fryer is controlled by conveyor speed and by chip bed depth. Bed depth matters because too deep a layer reduces oil contact and yields uneven color. Oil circulation is designed to keep temperature uniform across the fryer. Filters continuously remove crumbs and starch fragments that break off. Without filtration, crumbs burn and darken the oil, increasing dark specks and changing heat transfer. Oil turnover with fresh oil additions maintains consistent frying behavior over long runs. Before frying, slices go through a washing stage that controls surface starch. Freshly sliced potatoes release starch that forms a sticky film. If that film remains, slices stick together in the fryer and cook unevenly. The wash system uses flumes and sprays to remove free starch. Flow is tuned so slices separate without breaking. After washing, slices are dewatered on vibrating screens and with air knives. Removing surface water matters because water entering the fryer cools the oil locally and increases splatter and oil breakdown. Dewatering stabilizes fryer temperature and improves chip texture. Slice geometry is set at the slicer and influences every downstream step. Potatoes are fed into a high-speed slicer where a rotating blade cuts thin slices at a fixed thickness. Thickness is the primary determinant of crispness and color. Thinner slices cook faster and become very crisp, but can be fragile. Thicker slices cook slower and can remain slightly chewy if the fryer is not adjusted. The slicer uses sharp blades to create clean edges. Dull blades tear cells and create ragged surfaces that absorb more oil and shed more fragments. Many chip lines also apply slice sorting. A screen separates small fragments and slivers from full slices. Slivers fry faster and become darker, so removing them improves color consistency. Some lines also classify slices by thickness using optical measurement and divert out-of-range slices. Keeping thickness narrow allows fryer time and temperature to remain stable. The potato feed to the slicer is stabilized by upstream size grading. Potatoes arrive in bulk with variation in diameter and length. Large variations can cause feed surges and slicing inconsistency. A grader routes potatoes to appropriate lanes or rejects extremes. Feed hoppers and belts deliver a steady flow to the slicer, so blade load remains consistent. Consistent blade load produces consistent thickness. Raw potato preparation begins at receiving. Potatoes enter water flumes that transport them while removing stones and heavy debris in trap sections. Spray washers remove soil that would dull blades and discolor oil. Peeling is used on many lines. Abrasive peelers remove skin by rubbing against carborundum surfaces, while steam peeling can loosen skins quickly before mechanical removal. Peeling choice depends on product style. For classic thin chips, peeled potatoes provide uniform color and reduce dark spots. After peeling, potatoes are rinsed to remove peel fragments and then inspected by optical sorters that remove rotten spots and green areas that would fry dark and taste bitter. Temperature control begins early because potato temperature affects slicing and frying. Cold potatoes slice more cleanly and release less surface starch, but very cold potatoes can have higher reducing sugar levels from cold storage, which increases browning. The plant manages potato storage and tempering so raw potatoes arrive at a temperature that supports both slice quality and target color. Reducing sugar content is managed through raw material selection and sometimes through brief conditioning treatments. Potatoes with high reducing sugars brown too fast and produce dark chips. Wash and blanch steps are more common for fries than for chips, but some chip lines manage sugar through storage control and by blending lots. The goal is consistent color without relying on heavy downstream correction. After slicing and washing, the system focuses on gentle transport. Slices move through flumes and onto dewatering belts. The line avoids high drop heights because thin slices tear easily. Torn slices become fines and increase oil degradation in the fryer. Gentle transport reduces breakage and improves yield. The transition into the fryer is designed to avoid clumping. Slices are spread into a uniform layer before entering oil. Spreading can be done with distribution belts or vibratory feeders. A uniform entry layer ensures every slice sees similar oil contact and similar dwell time. producing uniform moisture removal and color. After frying, chips pass through a color sorting stage on many lines. Cameras measure chip color and eject overly dark chips with air jets. This stage compensates for occasional raw potato variability and fryer transient conditions. Sorting reduces the incidence of bitter dark chips in the bag and improves visual uniformity. Ferrero Rocher is manufactured by assembling a layered sphere where a roasted hazelnut sits inside a wafer shell. The shell is filled with hazelnut chocolate cream. Then the whole piece is coated in chocolate and rolled in chopped hazelnuts before a final set and wrap. The process starts with hazelnut preparation because nut size and roast level define the center bite and also influence how the coating adheres. Raw hazelnuts are cleaned with screens and air separation, so stones and shells are removed. The nuts are graded by diameter, so the center nut fits the wafer cavity without forcing cracks. Roasting line heats the nuts to a target color and moisture. Roasting drives off water and develops aroma while keeping the nut interior crisp. After roasting, the nuts are cooled quickly, so residual heat does not soften the wafer later. Skins are removed after roasting because loose skin fragments create bitter specks and interfere with cream texture. Nuts pass through rubbers or abrasive rollers that loosen skins. Air aspiration lifts skins away from the heavier nut kernels. The cleaned nuts are then re-screened to remove broken pieces. Whole nuts are routed to center insertion. Broken nuts are routed to chopped nut streams or paste production. A portion of the roasted nuts is chopped for the outer layer. Chopping is done with calibrated cutters that create a narrow size band. The target size must be large enough to read as crunchy pieces. The target size must be small enough to adhere evenly to a wet chocolate surface. Chopped nuts are screened to remove fines because fines create dust and dull the finish. The chopped nut stream is held in dry, conditioned air so it remains free-flowing. Another portion of the roasted nuts is processed into hazelnut paste for the cream and chocolate phases. Nuts enter a grinding system where rollers or stone mills reduce them to a smooth paste. Grinding generates heat, so the paste line uses temperature control to avoid over-thinning. The paste is refined until particle size is below the gritty threshold. The paste is then held in jacketed tanks with slow agitation to prevent oil separation. Wafer production runs as a separate stream because wafer must be crisp and dimensionally stable. Wafer batter is prepared by blending flour with water and sugar and small amounts of fat. Mixing is controlled to hydrate flour while limiting gluten development. The batter is filtered to remove lumps that would block depositor nozzles. Batter viscosity is adjusted so it spreads evenly on heated plates. Wafer baking uses wafer irons that form thin sheets by heating both sides. The batter is deposited onto the plates and spread into a uniform film. Heat drives water out quickly and sets the wafer into a rigid, porous sheet. Baking time is tuned so the sheet dries to low moisture without scorching. The sheet exits and is cooled so it becomes crisp and easy to cut. To create the Rocher shell, the wafer is shaped into cups or hemispheres. One method presses warm wafer sheets into molded cavities and then trims the edges. Another method bakes wafer directly into formed shapes using shaped plates. Forming must avoid cracks because cracks allow cream leakage. The formed halves are inspected by size and by edge integrity. Wafer halves are then paired into hollow spheres. A joining step applies a thin line of adhesive cream or chocolate along the rim. Two halves are aligned and pressed together. Pressure is controlled so the seam closes without crushing the wafer walls. The joined shells are cooled briefly so the seam sets and the sphere stays rigid during filling. The filling cream is produced as a fat-based emulsion with suspended solids. Sugar and milk solids are blended with hazelnut paste and cocoa components depending on the target profile. The mass is refined so it becomes smooth and spreadable. Refining can be done with roll refiners or ball mills that reduce particle size. The cream is then conched or mixed under heat to remove moisture and to distribute fat. Final viscosity is tuned so it can be dosed into wafers without air gaps. Chocolate used for coating is prepared and tempered for stable crystallization. Chocolate is melted and filtered to remove unmelted particles. Tempering cools the chocolate and builds stable seed crystals. The chocolate is then brought to a working temperature that maintains flow. Viscosity is adjusted by temperature control and by cocoa butter balance. Stable viscosity is needed because coating thickness must be consistent. Filling the wafer sphere begins by dosing a layer of cream into the cavity. The dosing head inserts into the shell opening and dispenses a controlled volume. The shell rotates or indexes, so cream spreads along the inner wall. This creates a base that will hold the center nut. The volume is controlled to avoid excess that would squeeze out at closure. A whole roasted hazelnut is then placed into the center. Placement uses a singulation system that feeds nuts one by one. Each nut is aligned and dropped into the cream bed. The cream supports the nut and locks it in position. Nut placement must be centered so the final sphere balances during coating. Off-center, nuts create wobble and uneven chocolate thickness. After nut placement, the cavity is topped off with more cream. The second dose surrounds the nut and fills remaining void volume. The dosing profile is tuned to avoid trapping air around the nut. Air pockets can collapse during cooling and cause surface dents. The cream surface is leveled, so the opening can be sealed cleanly. Sealing closes the filled sphere, so the cream is enclosed. A wafer cap or a chocolate plug can be applied depending on design. If a wafer cap is used, it is bonded with a thin film of cream and pressed into place. If a chocolate plug is used, tempered chocolate is deposited to create a seal. The seal must be strong enough to survive later tumbling and coating. After sealing, the filled spheres are cooled to firm the cream. Cooling brings the fat phase into a stable crystal state. It also reduces cream tack, so spheres do not stick during transfer. Cooling is staged, so wafer does not absorb condensation. Humidity control matters because wafer crispness must be preserved. Once the centers are stable, the line moves into chocolate enrobing. The spheres pass through a chocolate curtain or a dipping system. Chocolate coats the surface and also acts as the adhesive for chopped nuts. Excess chocolate drains off as the spheres roll on a wire belt. A controlled vibration can smooth the coating and release trapped bubbles. Air knives can trim excess and define a consistent thickness. Immediately after chocolate coating, the spheres enter a nut coating stage. Chopped hazelnuts are applied while the chocolate is still wet. The spheres roll through a bed of chopped nuts, or nuts are showered from above. Rolling ensures full coverage across the sphere. Nut feed rate is tuned, so coverage is dense but not clumped. Excess nuts fall away and are recirculated after screening. Nut adhesion depends on chocolate temperature and set speed. If chocolate sets too fast, nuts will not embed fully and will shed later. If chocolate sets too slow, nuts can slide and form bare patches. The process balances chocolate temper and cooling tunnel entry, so the surface remains tacky long enough for nut embedding. After nut application, the pieces enter a cooling tunnel that solidifies the chocolate. The cooling profile is staged to promote stable crystals. Early cooling sets the surface quickly, so nuts lock in place. Later cooling pulls heat out, gradually, to avoid contraction cracks. Final exit temperature is set, so pieces are hard enough for wrapping. During cooling, the internal cream also equilibrates. The cream fat network continues crystallizing and becomes firmer. This improves bite and reduces oil migration. Temperature stability prevents bloom risk and keeps the outer finish glossy. The wafer remains protected because the chocolate and cream act as moisture barriers. Some lines apply a final polish to reduce loose nut dust. A gentle tumbling or airbrushing step can remove unattached fragments. This step improves pack cleanliness and reduces debris in wrappers. It also reduces scuffing during downstream handling. Sorting and inspection occur before packaging. Vision systems can detect incomplete nut coverage and shape defects. Weight checks confirm fill and nut presence. Rejects are diverted so only uniform pieces reach wrapping. Metal detection can be used as a final integrity control. Cadbury chocolate begins as a controlled blend of cocoa components, dairy components, sugar, and fat that is refined into a smooth suspension, conched to stabilize flow and flavor, tempered to lock in stable crystals, then molded and packed, while temperature and viscosity stay inside a narrow window. Production starts with cocoa raw materials that arrive as beans or as processed cocoa ingredients, depending on the plant layout. When beans are used, they are cleaned first with screens and air separation, so stones and husk fragments are removed. The beans are then roasted in a programmed heat curve that drives off moisture and develops cocoa aroma while keeping scorch risk low. Roasting also makes the shells brittle, so separation is efficient later. After roasting, the beans are cracked and winnowed. Cracking breaks beans into nibs without pulverizing shells into fines. Winnowing uses airflow to lift lighter shell away from heavier nib. The nib stream is screened to remove oversized fragments that would strain grinders and to remove dust that would darken and overheat during milling. Nibs then enter grinding to become cocoa liquor. Grinding is a staged reduction where particle size drops while fat from the nib makes the mass flow. Early mills break nib into paste. Later mills refine the paste into a smoother liquor. Temperature is controlled because friction can raise heat and drive off aromatics. The goal is a stable liquor that is pumpable and consistent in solids and fat. Cocoa butter and cocoa powder streams are also managed. Cocoa butter is melted in jacketed tanks and filtered so no solid flakes remain. Cocoa powder is sieved to remove lumps that would create specks. These cocoa streams become levers for viscosity and flavor. More cocoa butter increases flow and melt. More cocoa solids increase intensity and thickness. Milk ingredients are prepared with the same attention to moisture and particle behavior. Milk powder is stored dry and sieved to break clods. Whey powders or lactose powders are handled similarly when used. These powders carry dairy flavor and also influence sweetness and caramel notes during later heating. Moisture in dairy powders must be low because water in chocolate drives thickening and seizing. Sugar is prepared as a clean, dry crystal feed. It is screened to control crystal size and remove agglomerates. Crystal size influences refining load and final mouthfeel. Fine sugar can reduce refining time but can increase dust and handling issues. Coarser sugar can slow refining and increase wear. The line selects a sugar specification that supports consistent refining performance. The first assembly stage is mixing, which creates a uniform pre-blend before refining. Cocoa liquor and melted cocoa butter enter a mixer and create a fat, continuous base. Sugar and milk powders are added gradually so they are wetted rather than floating as dry islands. Mixing uses a strong folding action to distribute powders through fat. The goal is a crumbly paste or thick dough depending on the recipe and the amount of fat present at this stage. In some milk chocolate processes, a crumb step is used to build characteristic dairy notes and to stabilize the milk solids. Crumb production combines milk and sugar with cocoa liquor or cocoa components and then heats the mixture to drive off water and develop flavor. The mixture is cooked until it becomes a dry or semi-dry crumb material. The crumb is then milled and later remelted into chocolate mass. This approach changes flavor and texture because it sets milk sugars in a different thermal history. Whether crumb is used or not, the downstream steps still require refining and conching. Refining is the step that turns the mixed paste into a smooth eating texture. Refining reduces the size of sugar and cocoa and milk particles so the tongue cannot detect grit. This is often done with 5-roll refiners or with alternative milling systems. In DUR, roll refining the paste passes between rollers with decreasing gaps. Each pass squeezes and shears particles smaller. The output becomes thin flakes because the mass leaves the final roll as a film that breaks off. Refined flakes have low free fat at their surface and are prone to holding moisture and air. They must be processed immediately into conching. Conching is a combination of mixing, shear, and controlled heat that changes both flavor release and rheology. In conching, the flakes are worked in a conche where paddles or rotors knead the mass. Heat keeps fat fluid and encourages volatile removal. Shear coats particles fully with fat, which reduces friction and lowers viscosity at a given fat level. Conching is often described as 2 overlapping goals. One goal is flavor smoothing by driving off unwanted volatiles and distributing aroma compounds. The second goal is flow control by reducing moisture and breaking down agglomerates so the chocolate becomes a stable suspension. Moisture control is critical because even small water content can cause thickening. Conches, therefore, manage airflow and temperature so water leaves gradually without overheating. During conching, emulsifiers can be added to fine-tune flow. Lecithin is a common flow modifier and it reduces yield stress by improving particle wetting. Another emulsifier can be used to reduce viscosity further at the same fat level. These additions are dosed late because early addition can mask conching effects and can change shear behavior. Dosing is precise because small changes alter how chocolate runs through pumps and through molding heads. After conching, the chocolate is held in storage tanks with gentle agitation. Tanks keep temperature stable, so the chocolate remains fluid. Agitation prevents separation and keeps the suspension uniform. Filters remove any foreign particles or unmelted lumps before tempering. At this stage, the chocolate is smooth and flavored, but it is not yet in the right crystal state for molding. Tempering is the controlled crystallization of cocoa butter that creates a stable set and a clean snap. Chocolate contains cocoa butter that can crystallize in several forms. Only specific forms give the desired gloss and contraction. Tempering builds a population of stable seed crystals and then holds the chocolate at a working temperature where these seeds guide solidification. Tempering is done in continuous tempering machines that heat and cool the chocolate in stages. The chocolate is first heated to melt existing crystals fully. It is then cooled while being agitated so crystals begin to form. It is then gently reheated to melt unstable forms while keeping stable seeds. The output is a chocolate that flows well, but contains the right crystal seeds. Process control uses temperature sensors and viscosity signals to maintain stability. Once tempered, the chocolate is ready for shaping. For bars, the main shaping method is molding. Polycarbonate molds move under deposit heads that meter chocolate into each cavity. The depositor fills to a precise mass because bar weight must be consistent. Molds then pass onto a vibrating table. Vibration removes trapped air bubbles and levels the surface. It also helps chocolate flow into sharp corners and improves surface gloss. After vibration, molds enter a cooling tunnel. Cooling is staged so the surface sets without shock. As chocolate cools, it contracts slightly. This contraction helps release from the mold. Cooling zones remove heat gradually so internal stress remains low. If cooling is too fast, the bar can warp or show bloom later. If cooling is too slow, throughput drops and molds remain occupied. When bars have solidified, they are demolded. Molds are flexed or tapped so bars release cleanly. The bars then move to inspection conveyors. Vision systems can detect surface defects and missing corners. Weight checks can confirm deposit accuracy. Defective bars are diverted for rework. Rework. Chocolate is collected and remelted, then reintroduced upstream in controlled ratios, so crystal history does not destabilize tempering. If the product includes inclusions like nuts or crisp pieces, the process adds an inclusion stage. Inclusions are prepared by roasting or drying and then screening to a tight size band. They are added either into the chocolate before molding or sprinkled into molds before depositing. Inclusion dosing must be consistent because it affects bar thickness and cooling time. Inclusion surfaces must be dry because moisture causes thickening and can create voids. If the product includes layered fillings, the line uses sequential depositing. A chocolate shell may be deposited first and partially set. A filling is deposited next. Another chocolate layer seals the top. This creates a composite bar that requires additional cooling time and more careful temper control. Even then, the same fundamentals apply. Each phase must flow at the right viscosity and set in the right order. Once bars are fully set, they move to wrapping. Wrapping is a mechanical process that protects chocolate from oxygen and moisture and from handling marks. Bars are fed into a flow wrapper or into a fold wrap system depending on the pack style. The wrapper forms film around the bar and makes seals. Seal temperature and dwell are controlled so the film closes without wrinkles. Film tension is controlled so it does not crush the bar edges. Tophye is manufactured by assembling a layered piece in a fixed cavity sequence, where a caramel cup is formed first, a hazelnut is seeded into that cup, a hazelnut cocoa cream is deposited around the nut, and a final chocolate cap is applied before cooling and tray packing. Production starts with preparing the two high-volume mass streams that define the piece. One stream is a caramel that must be firm enough to hold a cup shape, yet soft enough to bite cleanly. The other stream is a nut cream that must be smooth and pumpable, yet stable enough to keep its shape around the nut. A third stream is tempered chocolate for the cap and for any sealing functions. Caramel manufacturing begins with sugar and glucose syrup handling. Sugar is screened so crystal size is consistent and clumps are removed. Glucose syrup is held in jacketed tanks, so viscosity stays stable for accurate pumping. Dairy components are prepared as a controlled liquid or powder stream depending on the recipe design. Fat is melted and filtered so it can be kneaded smoothly into the cook. Cooking is done in a continuous cooker or a batch kettle that is designed for high solids confectionery. The syrup phase is heated to dissolve sugar and drive off water. Solids level is the key target because it controls final chew and flow at the depositor. If solids are too low, the caramel will slump in the mold and stick in tooling. If solids are too high, the caramel becomes glassy and cracks when formed into thin walls. Temperature and residence time are tuned so browning develops to the desired level without scorching. As the cook reaches endpoint, the caramel is cooled to a working temperature where it remains plastic. Cooling is staged so viscosity is stable across the run. The caramel is held in a jacketed tank with gentle agitation to prevent skin formation. This tank feeds the forming depositor through heated pipes that avoid cold plugs. Flow meters and pressure sensors keep the depositor feed steady. Hazelnut handling runs in parallel. Nuts are cleaned and graded so the size band matches the cavity. Roasting drives moisture down and develops aroma while keeping the nut crisp. Cooling follows immediately, so residual heat does not soften caramel or melt cream fats later. Skin removal reduces bitter flecks and improves adhesion in the cream stage. Whole nuts are then singulated so they can be placed one by one. The hazelnut cocoa cream is prepared as a fat, continuous paste. Roasted hazelnuts are milled into a smooth nut paste with controlled temperature so oil does not separate. Sugar and cocoa solids and dairy solids are blended into this paste. Refining reduces particle size so the cream feels smooth rather than gritty. The cream is then mixed under controlled heat so viscosity becomes consistent and air is minimized. Emulsifiers can be introduced to tune flow and prevent oil bleed. The finished cream is held warm enough to pump, but cool enough to keep flavor stable. Chocolate for the cap is produced and tempered to a stable crystal form. Chocolate is melted and filtered, so no unmelted fragments remain. It is then tempered in a continuous tempering unit that heats and cools in stages. The goal is a chocolate that flows well but sets fast with gloss and clean release. Viscosity is monitored because cap thickness depends on flow through small nozzles. Assembly begins on a tray or belt line that carries a field of cavities. The cavities act as the master geometry for the product. Each cavity receives each component in sequence with tight timing. The first operation deposits caramel into each cavity as a measured shot. The shot is designed to form a cup rather than a flat puddle. This is done by using nozzle geometry and deposit motion that pushes caramel up the cavity walls. Immediately after deposit, a forming tool can shape the caramel cup. A punch or dome tool presses into the caramel to create a bowl profile. Tool temperature is controlled so caramel does not smear or stick. Dwell time is short, so the line speed remains high. The tool retracts and leaves a consistent hollow with a defined rim thickness. Caramel cup geometry is a major control point. Wall thickness must be thick enough to hold during nut insertion. Wall thickness must not be so thick that the bite becomes overly chewy. Rim geometry must be clean because the rim later interfaces with cream and the chocolate cap. If the rim is uneven, the cap can sit crooked and leave gaps. After cup forming, the cavities pass through a short cooling section. This cools the caramel surface to increase strength for nut insertion. Cooling is tuned to firm only the surface layer while keeping the bulk plastic. A fully hardened caramel would crack when a nut is pressed in. A too soft caramel would allow the nut to sink and deform the cup. Nut insertion follows. Nuts are fed from a singulator that orients each nut. A placement head drops or presses one nut into each caramel cup. Placement force is controlled so the nut seats at a consistent depth. The nut must be centered so the final piece balances. Off-center nuts can create thin caramel walls that tear. The nut is pressed enough to anchor without breaking the nut. Next, the nut cream is deposited around the nut. The depositor nozzle enters the cavity and dispenses a controlled volume. The cream must flow around the nut and fill the annular space. It must also avoid trapping air under the nut or along the cup wall. To control air, the deposit can be staged as a first ring and then a top fill. The nozzle motion can trace a small circle to wet the wall evenly. Cream viscosity is tuned for this step. If the cream is too thin, it floods and can overflow the rim. If it is too thick, it bridges and leaves voids. Void formation is a defect because it weakens structure and creates visual gaps under the cap. The line controls cream temperature tightly because temperature is the fastest way to shift viscosity without changing formulation. After cream deposit, the surface is leveled. A small leveling blade or vibration can flatten the cream surface. Leveling ensures the chocolate cap will sit evenly. It also ensures the cap seals the cavity edge without a high spot that would break later. Leveling is gentle because excessive vibration can move the nut and distort the cream ring. Chocolate capping follows immediately after leveling. Tempered chocolate is deposited as a disc onto the cavity opening. The disc must bond to the cream and rim and then set without cracking. Deposit weight defines cap thickness, which controls snap and protects the interior. If the cap is too thin, it can fracture during tray packing. If too thick, it can dominate the bite and slow setting. To achieve a clean cap, the chocolate is deposited at a temperature where it spreads slightly, then stops. The mold geometry helps define the cap edge. Some lines use a light vibration after capping to remove bubbles and ensure contact. Vibration must be limited because it can cause chocolate to run down the cavity walls and change appearance. The industrial strawberry layer cake manufacturing sequence begins at the bulk dry storage terminal. Large-scale suction blowers move sifted pastry flour into the primary weight hoppers. These hoppers utilize load cells to ensure a precision of within 100 grams. A secondary pneumatic line introduces powdered glucose into the flour stream. The glucose prevents the starch from retrograding during the freezing process. Sodium bicarbonate is injected at a ratio of 2 kilograms per metric ton of flour. This leavening agent reacts with acidic components to create the crumb structure. A Z horizontal ribbon blender rotates to achieve a 99% homogeneity rating. The hydration phase starts inside a twin-screw continuous mixing unit. Liquid whole eggs are metered into the chamber at a constant flow rate. These eggs are chilled to 5 degrees Celsius to prevent protein denaturation. A high-pressure pump injects vegetable oil through a series of micro nozzles. The oil coats the flour particles to inhibit excessive gluten development. Deionized water is added to reach a specific gravity of 1.05 for the batter. A jacketed cooling system keeps the mixing chamber at a steady 18 degrees Celsius. This temperature control is vital for the stability of the chemical leavening agents. The aeration stage uses a high shear rotostator head to incorporate nitrogen gas. Nitrogen provides a finer bubble structure than standard atmospheric air. The resulting batter density is measured by an inline densitometer. This device sends real-time feedback to the gas flow controller. A batter density of 0.45 grams per cubic centimeter is the target for this recipe. The batter travels through stainless steel piping to the manifold depositor. This manifold spans the width of a 1 meter wide steel conveyor belt. Individual piston pumps discharge 60 milliliters of batter into silicone-coated molds. The molds move into a direct gas-fired tunnel oven with 12 independent heat zones. Zone 1 operates at 140 degrees Celsius to facilitate initial lift. The belt speed is calibrated to ensure a 20-minute residence time. Moisture sensors at the midpoint monitor the humidity levels of the oven atmosphere. High humidity prevents the formation of a thick crust on the sponge surface. Zone 6 reaches a peak temperature of 190 degrees Celsius. This heat triggers the caramelization of surface sugars for color development. The final zones gradually reduce the temperature to set the internal cake matrix. Automatic vacuum depanners lift the baked sponges from the molds at the oven exit. The sponges are placed onto a modular plastic cooling belt. This belt travels through a HEPA-filtered cooling tunnel for 30 minutes. Ambient air is pulled through the sponges to remove internal heat. The core temperature must reach 22 degrees Celsius before the slicing phase. A battery of reciprocating serrated blades cuts the sponges into 3 equal layers. The blade height is adjusted by microservos based on laser thickness measurements. Each layer is diverted to a separate conveyor for specific ingredient application. The strawberry coulis production wing operates as a closed-loop thermal system. Frozen strawberry blocks are pulverized by a high-torque industrial crusher. The resulting slurry moves into a vacuum evaporator to concentrate the natural sugars. Evaporation occurs at 60 degrees Celsius to preserve the volatile flavor compounds. Liquid pectin is injected into the concentrate to establish a thermoreversible gel. The pH is adjusted to 3.2 using a concentrated lemon juice buffer. This acidity is necessary for the pectin to form a stable molecular network. The coulis is then passed through a fine mesh filter to remove seeds. A plate heat exchanger cools the coulis to 8 degrees Celsius for immediate use. The first applicator station uses a waterfall distributor to coat the base layer. A weight check scale verifies that 40 grams of coulis are applied to each cake. The second sponge layer is placed on top by a high-speed vacuum pick-and-place unit. A second applicator deposits a layer of strawberry-infused cream over the middle sponge. This cream contains stabilized dairy fats and emulsified strawberry solids. The third sponge layer completes the vertical stack before the primary icing phase. The outer frosting is prepared in a pressurized aeration tank for maximum volume. Anhydrous milk fat is blended with sugar syrup and natural stabilizers. The mixture is whipped at 500 revolutions per minute under 3 bars of pressure. This process creates a stable foam with a shelf life of 12 days. The frosting is pumped to a dual-axis robotic icing station. The cake rotates on a pedestal while a side scraper applies the frosting. A top spreader levels the frosting to a thickness of 4 millimeters. Optical cameras inspect the coverage for any gaps or uneven patches. Decorative strawberry rosettes are formed by a multi-nozzle extrusion head. This head uses a star-shaped aperture to create the traditional fluted texture. The extrusion pressure is synchronized with the conveyor belt speed. A secondary station applies a fine mist of pectin glaze over the frosting. This glaze prevents the frosting from drying out during storage. Fresh strawberry quarters are placed into the rosettes by a vision-guided robotic arm. These strawberries are pre-treated with an ascorbic acid wash to prevent browning. A final dusting of pulverized dextrose is applied for visual contrast. The cakes enter a spiral blast freezer for rapid stabilization. Liquid carbon dioxide is sprayed into the chamber to reach minus 40 degrees Celsius. This rapid cooling creates small ice crystals to preserve the cake texture. The cakes spend 45 minutes inside the spiral freezer. An automated pusher arm moves the frozen cakes toward the packaging line. Cardboard flats are folded into boxes by a mechanical mandrel system. A plastic liner is inserted into each box to prevent moisture loss. The cakes are lowered into the boxes by a soft grip robotic hand. A metal detector scans every boxed cake for potential physical contaminants. This unit can detect ferrous particles as small as 0.5 millimeters. Any rejected boxes are diverted to a secondary inspection bin. A weight grader ensures the final product meets the 500-gram specification. The boxes are sealed with a tamper-evident adhesive strip. An inkjet coder prints the batch number and the production timestamp. The boxes are stacked into corrugated shipping cases by a robotic palletizer. These cases are then wrapped in polyethylene film for structural stability. The palletized goods are moved into the high bay cold storage warehouse. This facility uses an automated storage and retrieval system for inventory management. The temperature is maintained at minus 18 degrees Celsius with zero fluctuation. Loading docks are equipped with thermal seals to prevent heat ingress during shipping. Every delivery truck is monitored via GPS for real-time temperature tracking. This data is logged into the Quality Assurance Database for compliance. The entire production line can output 800 cakes per hour. This efficiency is achieved through the total integration of mechanical and digital controls. The cleaning in place system cycles through the entire piping network every shift. Hot caustic solution removes fat deposits from the mixing and pumping units. A secondary acid wash neutralizes any mineral scale in the heating elements. The final rinse uses sterilized water to ensure a zero residue environment. All wastewater is treated in an on-site filtration plant before discharge. This plant recovers 90% of the water for non-food industrial use. The factory operates on a 24-hour cycle to maximize equipment utilization. This rigorous process ensures the consistency of the industrial strawberry layer cake. The air quality in the assembly room is monitored for microbial counts. Surface swabs are taken from the conveyor belts every 4 hours. These samples are incubated in the laboratory to check for yeast and mold. The flour silos are equipped with explosion venting panels for safety. Dust collection systems pull fine particles away from the mixing stations. The grease used in the mechanical bearings is food grade certified. All electrical panels are NEMA rated for protection against high pressure washdowns. The facility utilizes LED lighting to reduce heat generation in the cooling zones. The vegetable oil is stored in nitrogen-blanketed tanks to prevent oxidation. These tanks are equipped with ultrasonic level sensors for inventory tracking. The sugar syrup is kept in heated vats to prevent crystallization. All raw ingredients are barcoded upon entry for full traceability. This allows the factory to track a single cake back to the specific wheat harvest. The conveyor motors utilize variable frequency drives for precise speed control. These drives reduce energy consumption during periods of lower production. The central control room monitors every motor and sensor in the building. The robotic arms are programmed using a proprietary motion control language. These programs allow for rapid changeovers between different cake sizes. The ultrasonic blades are sharpened using a specialized grinding unit every weekend. This maintenance ensures the cleanest possible cut for the sponge layers. The silicone molds are inspected for surface degradation after every 1,000 cycles. Worn molds are recycled to prevent any silicone migration into the batter. The packaging cardboard is sourced from sustainably managed forests. This commitment to materials ensures the long-term viability of the production model. The industrial fabrication of brownies begins with the high-volume intake of raw commodities. Bulk storage silos hold up to 50 tons of specialized pastry flour. This flour features a low protein content to ensure a tender crumb. Pneumatic transport lines move the flour into the primary sifting station. Vibratory screens remove any particles larger than 200 microns. Cocoa powder arrives in hermetically sealed containers to prevent moisture absorption. This cocoa is typically alkalized to reach a pH level of 7. The alkalization process darkens the powder and mellows the flavor profile. Automatic scales measure the cocoa with an accuracy of 10 grams. A separate line delivers granulated sucrose from a central hopper. The sugar is pulverized into a fine mesh to facilitate rapid melting. Liquid fats are stored in stainless steel vats with internal heating coils. These coils maintain the fat at a constant 45 degrees Celsius. This temperature prevents the lipid chains from crystallizing in the pipes. Refined soybean oil provides the necessary moisture for a fudgy texture. Some formulations utilize anhydrous milk fat for a richer mouthfeel. The primary mixing phase utilizes a high-torque industrial blender. The liquid fats enter the mixing chamber through pressurized nozzles. Cocoa powder is added next to create a thick chocolate paste. This stage is known as the wet rub in the baking industry. The friction from the blades raises the paste temperature slightly. Infrared sensors monitor this heat to prevent scorching of the cocoa. A secondary mixer prepares the hydration base for the batter. Liquid eggs are pumped from refrigerated tanks at 4 degrees Celsius. These eggs undergo inline pasteurization before they reach the blender. A plate heat exchanger flashes the eggs to 60 degrees Celsius. They are immediately cooled back to 10 degrees Celsius. This process eliminates pathogens without coagulating the egg proteins. Natural humectants, like vegetable glycerin, are added to the egg mix. Glycerin binds water molecules to the starch during the baking cycle. This chemical bond prevents the brownie from becoming stale. The dry ingredients meet the wet base in a continuous mixer. The flour is folded in by a twin-screw agitation system. This system prevents the overdevelopment of gluten in the wheat. Excessive gluten would make the brownie tough and bread-like. Salt is injected into the stream at a precise 0.2% ratio. It acts as a flavor enhancer for the chocolate components. A small amount of sodium bicarbonate provides a chemical lift. This leavening agent reacts with the acidic cocoa particles. The batter moves through a series of refining rollers. These rollers reduce the particle size of the sugar and cocoa. A final particle size of 30 microns ensures a smooth mouthfeel. The refined batter is pumped into a vacuum de-aeration tank. This tank removes any trapped air bubbles from the mixing stage. Removing air increases the density of the final brownie slab. A dense structure is required for the fudge classification of the product. The batter reaches a final viscosity of 15,000 centipoise. Industrial brownies often feature inclusions like semi-sweet chocolate chips. These chips are stored in a climate-controlled room at 18 degrees Celsius. This prevents the chips from blooming or sticking together. A vibratory feeder dispenses the chips into the moving batter line. A static mixer folds the inclusions in without shearing them. The ratio of inclusions is usually 10% of total weight. The batter is now ready for the depositing stage. A high-speed manifold spans the width of the production conveyor. This manifold contains 24 individual piston-driven nozzles. The nozzles deposit the batter into large steel baking trays. These trays are coated with a permanent Teflon layer. An automated sprayer applies a secondary film of vegetable oil. The oil ensures a clean release after the cooling phase. Each tray receives exactly 12 kilograms of brownie batter. Optical sensors verify the weight and level of every tray. A mechanical oscillating plate spreads the batter to the corners. This ensures the brownie slab has a uniform thickness of 30 millimeters. The trays enter a multi-zone convection tunnel oven. The oven is 60 meters long to accommodate high-speed production. It is heated by a series of natural gas burners. The first zone is set to 150 degrees Celsius. This initial heat initiates the melting of the sugars. The second zone increases the temperature to 170 degrees Celsius. This is the primary, baking phase where the structure sets. Convection fans circulate the air at 5 meters per second. This constant airflow ensures the edges do not burn before the center. Steam injection ports maintain a 40% humidity level. The humidity prevents the top surface from cracking or crusting. The final oven zone facilitates the Maillard reaction. This chemical reaction occurs between the sugars and amino acids. It creates the complex flavor profile associated with baked chocolate. The total residence time in the oven is 28 minutes. An automated arm extracts the hot trays at the oven exit. The trays move onto a modular plastic cooling belt. This belt travels through a spiral cooling tower. Filtered air at 15 degrees Celsius blows across the trays. The cooling process must be gradual to prevent the slab from shrinking. The internal temperature must drop to 25 degrees Celsius. This cooling phase typically lasts for 45 minutes. A vacuum depanner lifts the entire brownie slab from the tray. The slab is placed onto a high-density polyethylene cutting board. This board moves toward the ultrasonic slicing station. Ultrasonic blades vibrate at 20,000 Hz per second. This vibration prevents the dense brownie from sticking to the knife. The blades make vertical and horizontal cuts simultaneously. This creates perfectly square units with sharp edges. The standard size is 5 centimeters by 5 centimeters. Any trim from the edges is diverted to a rework bin. This trim is ground up for use in other chocolate products. The individual brownie units are separated by a divergent conveyor. This conveyor increases the space between the brownies for packaging. Some brownies pass through an enrobing station for a chocolate coating. The enrober pours a curtain of tempered chocolate over the units. A blower clears the excess chocolate to maintain a thin layer. The coated brownies enter a secondary cooling tunnel. This tunnel sets the chocolate coating to a high gloss finish. The brownies move into the primary packaging zone. A robotic arm picks up 4 brownies at a time. It places them into a pre-formed plastic blister tray. The tray provides structural support during shipping and handling. A flow wrap machine encapsulates the tray in a polymer film. This film is treated with a nitrogen flush. Nitrogen replaces the oxygen to prevent the oxidation of fats. This gas flushing technique doubles the product's shelf life. The film is heat sealed at both ends by a rotating jaw. A laser printer applies the lot number and expiration date. The individual packs move toward the secondary packaging station. A case packer assembles 24 packs into a corrugated box. This box is sealed with a pressure-sensitive adhesive tape. A check weigher verifies that the case meets the target weight. Any underweight cases are automatically pushed off the line. A palletizing robot stacks the cases onto a wooden pallet. The robot follows a specific pattern to ensure stack stability. A stretch wrap machine secures the load with several layers of plastic. The pallet is tagged with a radio frequency identification label. This label contains the entire production history of that batch. The pallets are moved to a temperature-controlled warehouse. This warehouse is kept at 18 degrees Celsius. Quality control technicians perform a moisture analysis on every batch. They use a halogen moisture analyzer to check for consistency. The target moisture content for a fudge brownie is 12%. A texture analyzer measures the force required to compress the brownie. This ensures the chewiness meets the brand specifications. The cocoa solids are verified using a spectrophotometer. This device measures the light absorbance of the chocolate. The production line operates on a 24-hour schedule. A clean-in-place system sanitizes the mixes between batches. This system uses hot water and biodegradable and detergents. All water used in the plant undergoes reverse osmosis filtration. The factory utilizes a closed-loop energy recovery system. Heat from the ovens is captured to preheat the incoming air. This reduces the carbon footprint of the manufacturing facility. The flour silos are equipped with explosion suppression systems. Fine flour dust can be highly combustible in large volumes. Spark detectors monitor the pneumatic lines for any heat buildup. The packaging room is kept at a positive air pressure. This prevents any dust or insects from entering the clean zone. Workers wear specialized lint-free suits and head coverings. All tools are made from detectable stainless steel. The vegetable oil tanks are nitrogen blanketed to prevent rancidity. Oxygen is the primary enemy of long-term fat stability. The supply chain is tracked using a digital ledger system. Every ingredient can be traced back to its original farm. This level of transparency is standard for industrial food. Production. The brownie recipe is stored in a secure digital vault. The central computer controls every motor and valve in the plant. The automated manufacturing of cheesecake begins with the large-scale processing of the base crust material. Bulk quantities of graham flour and wheat flour are combined in a high-speed industrial shredder. This unit pulverizes the baked biscuits into a uniform crumb with a diameter of 2 millimeters. The crumbs are moved via a vibratory conveyor to a horizontal blending drum. Molten butter is injected into the drum through a series of atomizing nozzles. The butter acts as a binding agent to ensure the crust remains structurally sound. Granulated sugar is added to the mixture to facilitate caramelization during the baking stage. The crust mixture is transferred to the primary molding line, by a vacuum lift system. Circular spring-form pans move along a specialized belt at a rate of 40 units per minute. A volumetric depositor drops exactly 100 grams of the crumb mixture into each pan. A pneumatic tamping head descends to compress the crumbs with 50 pounds of pressure. This compression creates a dense and level foundation for the cheese filling. The sides of the pans are simultaneously brushed with a light film of release agent. This prevents the cake from adhering to the metal during the cooling phase. The preparation of the cheese filling occurs in a separate, climate-controlled mixing terminal. Industrial-sized blocks of cream cheese are loaded into a vertical, high-shear mixer. These blocks are tempered to exactly 20 degrees Celsius to ensure maximum pliability. A heavy-duty agitation arm breaks the cheese down into a smooth and aerated paste. Liquid sour cream is introduced through a flow-controlled piping network. The sour cream provides the necessary acidity to balance the richness of the fats. Large quantities of liquid whole eggs are then metered into the mixing chamber. These eggs act as the primary emulsifier and structural setting agent for the batter. Pure vanilla extract is injected into the stream via a micro-dosing pump. The mixing speed is reduced to avoid the over-incorporation of atmospheric air. Excess air in the batter causes the cheesecake to crack during the thermal expansion phase. The batter is monitored by an inline viscometer to ensure it reaches 4,000 centipoise. A final stage of the mixing process involves the addition of cornstarch. The starch binds to the free moisture to prevent the occurrence of syneresis. The finished batter is pumped through insulated stainless steel lines to the depositing station. A multi-piston manifold accurately dispenses the batter over the prepared crust. Each pan is filled to 90% of its total volume to allow for expansion. The pans are then transferred into a continuous water bath tunnel oven. This oven utilizes a shallow pool of circulating water to regulate the heat transfer. The water bath ensures the temperature never exceeds 100 degrees Celsius at the base. This thermal regulation prevents the edges of the cake from cooking faster than the center. The oven is divided into 4 distinct thermal zones for precise moisture control. Zone 1 maintains a high humidity level of 80% to prevent surface drying. The temperature in this initial stage is set to 120 degrees Celsius. Zone 2 increases the heat to 140 degrees Celsius to set the egg proteins. The moisture levels are gradually reduced in Zone 3 to facilitate color development. A light golden hue is achieved on the surface through controlled convection airflows. The final zone utilizes a cooling gradient to stabilize the cake before it exits the oven. The total residence time within the tunnel oven is approximately 90 minutes. An automated arm removes the pans from the water bath at the end of the line. The cakes enter a primary cooling chamber to reduce the internal temperature to 40 degrees Celsius. This slow cooling prevents the cheesecake from pulling away from the sides of the pan too quickly. The pans move into a blast chiller where the temperature is dropped to 4 degrees Celsius. This rapid cooling stage is essential for the final set of the dairy fats. The cheesecake must reach a firm consistency before the depanning process begins. A mechanical depanner uses a series of gentle suction cups to lift the cake from the mold. The springform rings are automatically expanded and retracted for sterilization. The cakes are placed onto a sanitized plastic transport disc for the finishing stage. Many industrial cheesecakes receive a fruit-based topping at this point in the sequence. A secondary manifold applies a layer of fruit puree or glaze to the top surface. The glaze is heated to 60 degrees Celsius to ensure a smooth and glass-like finish. It is immediately cooled by a localized cold air jet to lock the topping in place. If the recipe requires a swirl pattern, a robotic needle system is utilized. The needles inject colored fruit syrups into the wet batter before the baking stage. The robotic arm follows a pre-programmed geometric path to ensure visual consistency. For decorative borders, a multi-nozzle whipping station applies cream cheese frosting. The frosting is extruded through fluted tips to create a traditional rosette pattern. The cakes then move to the high-frequency ultrasonic slicing station. The ultrasonic blades vibrate at 30,000 Hz to prevent the cheese from sticking. This technology allows for perfectly clean cuts through the dense and sticky filling. The machine can slice the cheesecake into 12 or 16 equal wedges. Each wedge is separated by a thin piece of parchment paper to prevent re-adhesion. The parchment paper is fed from a continuous roll and cut by the same blade. The sliced cakes are moved to the primary packaging terminal by a synchronized conveyor. The packaging process involves placing the cake into a rigid plastic dome. This dome protects the decorative frosting and the delicate top glaze. A cardboard base provides structural support and contains the product information. The packages are moved into a vacuum sealing machine to remove excess oxygen. An inert gas flush is sometimes used to maintain the freshness of the dairy components. The sealed units are then placed into individual retail boxes by a pick-and-place robot. These boxes are constructed from high-grade recycled paperboard with a moisture barrier. A laser printer applies the batch code and the specific expiration date to each box. The boxes are grouped into master cases for bulk distribution to wholesalers. Each master case is tracked by a unique radio frequency identification tag. The cases are stacked on pallets by a heavy-duty robotic palletizing arm. The pallets are wrapped in multiple layers of clear stretch film for stability. The finished product is stored in a deep freeze warehouse at -20 degrees Celsius. This freezing stage allows for long-distance transport without compromising the texture. The quality control department monitors the fat content of every batch using a centrifuge. The moisture to solids ratio is checked using a rapid thermal analyzer. Any batch that falls outside of the 5% variance range is rejected. The pH level of the batter is measured to ensure the sour cream has reacted correctly. A texture analyzer probes the center of a sample cake to measure the resistance. This ensures the mouthfeel is consistent across every single production run. The color of the top glaze is verified using a digital spectrophotometer. The industrial facility uses a centralized control system to manage the ingredient flow. Silos are equipped with ultrasonic level sensors to trigger automatic reordering. The water used in the process undergoes a 3-stage purification sequence. This includes carbon filtration and ultraviolet sterilization to ensure purity. The air in the assembly room is filtered through a series of HEPA units. These filters remove nearly all airborne contaminants from the production environment. The floors are sloped to integrated drainage systems for easy cleaning. Every 4 hours, the entire line undergoes a localized sanitation cycle. High-pressure steam is used to clean the depositor nozzles and mixing blades. The conveyor belts are constructed from antimicrobial blue polyurethane material. This material resists the growth of bacteria and is easy to inspect visually. The factory operates on a 24-hour schedule with 3 shifts of workers. The output can reach several thousand units per hour depending on the cake size. This massive scale is necessary to meet the global demand for frozen desserts. The supply of cream cheese is delivered via refrigerated tanker trucks. These tankers are emptied into the holding vats using a pressurized air system. The butter is stored in a separate heated room to maintain a liquid state. All dry ingredients are passed through a metal detector before entering the mixer. This ensures that no foreign objects from the harvesting process remain in the flour. The packaging materials are stored in a dry zone to prevent mold growth. The logistics team coordinates the departure of refrigerated trucks every 6 hours. Salmon production begins immediately after harvesting with rapid transport of whole fish to processing facilities. The fish are received in chilled holding tanks or insulated containers with ice slurry, where temperature is maintained near 0 degrees Celsius to minimize enzymatic activity and microbial growth. Once unloaded, the fish are fed into a de-icing flume system, where circulating chilled water removes surface ice and any external debris. After de-icing, fish are conveyed by stainless steel belt or pneumatic water transport to the grading station. Grading machines use load cell-equipped conveyor belts or camera-based systems to categorize each salmon by weight class and body dimensions. Size data is recorded and used to assign each fish to a specific processing line depending on target product specifications. Following grading, salmon are transferred to stunning and bleeding stations. Here, automated percussive or electrical stunning devices render the fish unconscious in under 1 second. Immediately after stunning, a rotary knife or fixed blade system incises the gill arch. The fish then enter a bleeding tank or conveyor where they are held for 5-10 minutes in chilled water to drain blood via circulatory pressure, improving flesh appearance and shelf life. Next is deheading and gutting, where fish are positioned by automated orientation systems to align uniformly before high-speed rotary blades remove the head. The carcasses pass through a ventral incision machine where circular or V blades open the abdominal cavity. Viscera are extracted using vacuum suction nozzles or mechanical scrapers. Internal membranes are further removed by pressurized water jets aimed at the peritoneal cavity. A water flusher system removes residual debris. Eviscerated salmon proceed to the trimming section, where trained operatives or automated vision-guided blades remove the kidney line, dorsal fin remnants, and any remaining membrane tissues. Machine-assisted trimming modules use camera detection and robotic knives for precision cuts at high speed. Visual scanners inspect the cavity for any leftover material. After trimming, fish are re-washed using chilled, potable water from multiple spray nozzles. Washed carcasses are fed into a filleting machine. This equipment uses belt-fed positioning and blade pairs to cut along the spine, separating the two fillets. These blades are height adjusted based on pre-scanned fish dimensions to ensure optimal yield. The resulting fillets are guided into discharge lanes, while frames and collars are diverted to co-product processing. Post-filleting, fillets move to a pin bone removal station. This step is performed using mechanical bone pullers with rotating rubber wheels and suction extraction. The system identifies bone position based on predefined muscle anatomy and removes intermuscular bones without damaging the surrounding flesh. Depending on line setup, bone removal can also be conducted manually with tweezers for premium products. Fillets then pass through trimming belts, where tail tips, belly flaps, collar edges, and skin tears are removed. Trimming can be configured based on customer specification. Camera-based sorting systems ensure uniformity, and deviations trigger diverters to reroute products for manual correction. The next stage is skin removal. Skinning machines feed fillets into a blade interface that separates the skin from muscle while minimizing meat loss. Blade pressure, feed rate, and depth of cut are adjusted via servo control systems. Some processing lines retain the skin for specific markets or product forms. After skinning, fillets are conveyed to portioning systems. Portioning is carried out with water jet cutters, ultrasonic blades, or mechanical slicers. Laser-guided mapping scans the fillet to define weight and shape. Cutting systems then divide the fillet into precise portions according to program parameters, such as fixed weight steaks, loins, or saku blocks. Cut portions are collected in synchronized lanes for immediate packing. In parallel, whole fillet lines bypass the portioning system. These fillets are passed through grading systems based on fat line visibility, color, and size. Multi-sensor units evaluate each fillet with color cameras, near-infrared sensors, and weight scales. Graded fillets are sorted into categories and routed accordingly. Chilling is applied before packaging. Fillets and portions are passed through a spiral or tunnel chiller where they are cooled with cold air or flaked ice mist to reduce core temperature to below 2 degrees Celsius. Chilling units use digital thermostats and humidity sensors to maintain consistent internal environment and airflow. Once chilled, the product enters the packaging zone. Here, fillets and portions are loaded into trays or vacuum pouches. Modified atmosphere packaging is commonly used, where oxygen is displaced and replaced with CO2 and N2 in precise ratios to extend shelf life. Gas mixtures are controlled by flow meters and validated with gas analyzers. Trays are sealed with lidding film using heat sealing units that ensure proper adhesion and headspace control. Vacuum packaged products are loaded into form-fill seal machines, which mold film around the product, evacuate air, and seal the pack in a continuous motion. Vacuum level, seal time, and film tension are PLC controlled. Pack integrity is tested using pressure decay sensors or inline leak detection systems. After packaging, units proceed to labeling and coding. Print and apply labelers affix product labels with weight, species, origin, and batch codes. Inkjet or laser coders apply best before dates and traceability codes on film or trays. Optical scanners verify label placement and print clarity. Packaged products are then grouped into secondary packaging units. Collating conveyors align packs for insertion into cartons or crates. Case packers load these into pre-formed boxes. Automated box sealers apply tape or glue to secure the cartons. Tertiary barcodes are printed for shipping and scanned for inventory integration. Sealed boxes are routed to palletizing cells. Robotic palletizers stack boxes according to predefined patterns using vacuum heads or fork grippers. Pallets are wrapped with stretch film and labeled with shipment data. Each pallet is scanned and assigned a warehouse location in the inventory management system. Cold chain is maintained throughout, with temperature sensors on conveyors, in holding rooms, and inside chilling units. Deviations trigger alerts and system flags. Data is logged and linked to each batch for traceability. End product temperatures are sampled using calibrated probes to verify compliance. Co-product handling operates in parallel. Salmon heads, frames, belly trims, and skin are collected separately. Heads and frames are directed to fish meal or oil extraction. Trimmed bellies may be sorted for smoking or mincing. Skins are graded and can be air-dried or frozen for export. All co-products are processed using stainless steel conveyors, crushers, or mincers with washdown capability. Smoking lines, if present, begin with brining or dry salting. Fillets are conveyed to tumblers or brine tanks, where salt concentrations and immersion time are automated. After salting, fillets are dried in humidity-controlled rooms before entering the smokehouse. Smoke is generated from wood chips or liquid smoke atomizers. Parameters such as smoke density, temperature, and air velocity are digitally controlled. After smoking, fillets are cooled and sliced using parallel slicers calibrated for thickness. In freezing operations, portions or fillets are directed to spiral freezers or contact plate freezers. Products are loaded onto stainless steel belts that pass through cold chambers at -35 degrees Celsius to -45 degrees Celsius. Dwell time is adjusted for product thickness to reach core temperatures below -18 degrees Celsius. Frozen products are bagged and sealed before moving to cold storage. Steak production begins after the animal carcass is chilled post-slaughter. Carcasses are held in cold storage rooms at 0 degrees Celsius to 2 degrees Celsius for 24 to 48 hours to complete rigor mortis and stabilize muscle structure. After this phase, the chilled sides are moved to the fabrication area using overhead rail systems equipped with trolleys. The first step is primal cutting. Sides of beef are placed on breaking tables and cut into primal sections using bandsaws and large breaking knives. The carcass is separated into forequarter and hindquarter at the 12th and 13th rib. The forequarter includes the chuck, brisket, rib, and plate, while the hindquarter contains the loin, round, and flank. From the hindquarter, the loin primal is isolated, which contains the strip loin, tenderloin, and short loin, common sources for high-grade steak cuts. The rib primal from the forequarter contains the ribeye section. Each primal is weighed, tagged with traceability information, and placed into designated bins or hooks. Primal sections are then moved to the boning line. Here, trained operators or automated knife systems remove bone structures. For ribeye and strip loin, the chine bone, feather bones, and spinal processes are removed using powered wizard knives or mechanical boning blades. Tenderloins are peeled away from the lumbar region with membrane knives, preserving the natural shape and minimizing yield loss. After deboning, cuts proceed to surface trimming, where external fat, silver skin, and connective tissues are removed. Precision trimming is performed using hand tools or vision-guided trim robots. Final trim levels are determined by target specifications, such as 1 4-inch fat cap or lean trim. The trimmed subprimals are transferred to aging rooms or directly to portioning, depending on the program. If aged, subprimals are vacuum packed using thermoforming machines and stored under controlled conditions at 0 degrees Celsius to 2 degrees Celsius for wet aging. Typical wet aging periods range from 14 to 28 days, depending on product line. Aged subprimals are retrieved and conveyed to the portioning area, where they are unpacked and visually inspected. Excess purge is drained, and the product is patted dry if needed to ensure consistency during slicing. Subprimals are loaded onto scanning tables equipped with 3 D-laser or X-ray systems. These systems analyze dimensions, fat distribution, and muscle structure to optimize cutting paths. Based on scan data, subprimals are transferred to automated steak portioning machines. These use rotating circular blades or water jet cutters to slice steaks at consistent thickness and target weight. Blade systems are servo-controlled to adjust angle and pressure in real time, compensating for shape variability. Common cut configurations include ribeye steaks, strip steaks, T-bone, porterhouse, sirloin, filet mignon, and top blade flat iron. Each type is portioned according to thickness specifications, typically ranging from 12 mm to 38 mm, and target weight tolerances within +1%. Cutting yield and number of steaks per subprimal are calculated live by onboard processors. Each steak is then conveyed to a weighing and grading station. Individual steaks pass over in-motion scales to confirm net weight. High-resolution imaging systems evaluate marbling score, surface integrity, and lean color. Grading software assigns visual quality rankings, and steaks are automatically sorted into output lanes based on specification match. Steaks requiring tenderization are routed through mechanical tenderizing machines. These consist of rotating blade rollers that pierce the muscle to sever connective fibers without altering surface appearance. For certain cuts like top round or sirloin, multiple passes may be used to reach the desired tenderness level. At this stage, enhancement or marination systems can be applied. For value-added products, steaks are loaded into vacuum tumblers or injector systems. Vacuum tumblers rotate the meat with liquid solution containing water, phosphate, salt, and flavoring. Injectors use multi-needle heads to evenly distribute brine through muscle fibers at defined pickup rates. Enhanced steaks are rested in staging bins for a defined soak period, then reweighed to verify target pickup has been achieved. Stricter control is maintained for fixed weight packs, where brine gain must fall within narrow tolerances to avoid over or under packaging. From here, steaks are conveyed into the packaging line, For fresh retail presentation, steaks are placed into polystyrene trays with absorbent pads and conveyed under MAP systems. Trays enter a sealing unit where oxygen is displaced with gas mixtures and overwrapped with clear lidding film. For vacuum-sealed steaks, portions are transferred to form-fill-seal machines. In these systems, bottom web film is thermoformed into pockets, steaks are loaded manually or robotically, and top film is vacuum sealed over the product. Seal bars apply pressure and heat to ensure consistent seal quality. Vacuum sealed steaks, intended for frozen distribution, are routed immediately to spiral or plate freezers. Steaks are individually frozen to core temperatures below 18 degrees Celsius in 30-60 minutes, depending on thickness. Frozen steaks are then bagged or boxed in bulk, with barcode labels applied for inventory tracking. Finished packs pass through metal detection and weight verification systems. Inline metal detectors scan for stainless, ferrous, or non-ferrous contaminants, rejecting non-conforming packs. Checkweighers confirm that net weight falls within compliance range. Data is logged to the MES system and linked to batch production ID. Packs are labeled with product name, weight, grade, origin, and expiry using thermal inkjet printers or automatic label applicators. Optical sensors ensure correct label application, alignment, and data accuracy. Invalid or missing labels trigger rejection and pack removal. Labeled steaks are grouped using robotic case packing systems. Retail packs are placed in corrugated shippers or RPCs, arranged according to order profiles. Case formers and glue applicators prepare cartons, which are sealed and labeled with GTIN, lot, and dispatch codes. Cases are moved to palletizing stations, where robotic arms stack them into predefined patterns on wood or plastic pallets. Pallets are then wrapped in stretch film for load stability and scanned into inventory management systems. Each pallet is assigned a location in chilled or frozen storage, depending on product type. All processing zones are monitored with environmental sensors. Temperature, humidity, and air velocity are logged continuously. Conveyor speeds, blade RPMs, cut counts, and yield rates are tracked via PLCs connected to a central SCADA system. Downtime, throughput, and machine error logs are accessible in real time. Quality assurance procedures include destructive sampling and analytical testing. Random steaks are removed and evaluated for marbling score, thickness, weight accuracy, pH, water holding capacity, and sensory characteristics. Steaks are cooked under controlled conditions to assess texture, flavor, uniformity, and juiciness. Chicken strip production begins with the reception of chilled, deboned chicken meat, typically composed of boneless breast fillets. These are transported in bulk containers from upstream slaughter and deboning facilities. On arrival, the meat is inspected for temperature compliance, then tipped into stainless steel hoppers for transfer into the cutting line. Chicken fillets are conveyed to the portioning section, where they are aligned on belts and scanned by high-resolution cameras coupled with laser or X-ray systems. These scanners detect size, shape, and internal structure. Data is processed in real time to guide waterjet or blade-based cutters that slice each fillet into uniform strips based on predefined weight, length, and thickness tolerances. Strips are conveyed into a trimming and inspection zone. Here, off-spec pieces, connective tissue, and surface fat are removed by automated blade systems or manually trimmed depending on the processing setup. A secondary vision system performs quality control on the stripped portions, ejecting defective pieces using pneumatic nozzles. Trimmed strips move into the marination system. The marination line consists of tumbling drums or vacuum massagers. Strips are loaded into the drum, which rotates while marination solution is injected or poured in. Marinade is typically a blend of water, salt, phosphates, modified starches, and flavor compounds. Ingredient mixing tanks feed the drum with chilled solution via peristaltic or centrifugal pumps. Drums operate under partial vacuum or atmospheric pressure depending on marination type. Vacuum assists protein extraction and enhances moisture retention. Tumbling speed and duration are controlled digitally, typically operating at 612 revolutions per minute for 15, 25 minutes. Finished marinated strips are discharged onto dewatering belts to remove excess surface marinade. Moisture-adjusted strips are conveyed into the coating system, a multi-stage line that applies a breading or batter system to each piece. The first stage involves pre-dusting, where strips are evenly coated with dry flour or modified starch powder to improve batter adhesion. Pre-dusting is applied via vibratory sifters and curtain feeders with excess powder removed by air blowers. Coated strips proceed to the battering station, where they pass through a liquid bath consisting of water, wheat flour, leavening agents, gums, and spices. Batter is recirculated continuously through inline filtration and agitation systems to maintain uniform viscosity. Strips are submerged using conveyor paddles, then raised through a vibrating belt to allow excess batter to drip off. Next is the breading application. Strips are dropped into a bed of dry breading mix, which may consist of breadcrumbs, cornmeal, or tempura crumbs. Top and bottom conveyors press breading into the meat surface. Breaders feature reflow systems that recirculate unused coating material after sifting out fines. Compressed air jets remove excess coating. For products requiring double coating, the batter and breading stages are repeated with a secondary set of machines, typically using coarser crumb materials for texture variation. Each station is monitored for line speed, dwell time, batter pickup, and breading adhesion. Strips then enter a setting fryer or pre-fry system. The setting fryer contains oil heated to 180-200 degrees Celsius and is typically 10-30 seconds in duration. This step partially cooks the outer coating to fix structure and prevent loss during freezing. Fryer oil is continuously filtered and circulated to maintain clarity. Exit temperature and surface moisture are measured in line. Post-fry, strips are transferred to a cooling conveyor that uses forced ambient or chilled air to reduce product temperature to under 30 degrees Celsius. Cooling prevents condensation in the next stage and prepares the surface for freezing. Conveyors are made of mesh belts for air penetration. Air velocity and temperature are controlled to stabilize product dimensions. Cooled strips are arranged in rows and conveyed into the freezing tunnel. Spiral or linear IQF freezers are used. Inside the tunnel, product is exposed to high velocity air at temperatures between 35 degrees Celsius and 45 degrees Celsius. Belt speed and airflow are calibrated to bring the product core temperature below 18 degrees Celsius within 15-25 minutes. IQF technology ensures each strip remains separate by using belt vibration, cryogenic burst, or pre-chill alignment. Ice accumulation and belt defrosting are controlled via automated heat pulse cycles. Tunnel freezers are cleaned in place and monitored for temperature uniformity. Once frozen, strips enter the weighing and sorting station. Multi-head weighers mounted above packaging lines portion strips into programmed weight ranges. Optical or X-ray systems recheck for foreign materials, bone fragments, or density anomalies. Rejected product is diverted automatically. Weighed portions drop into bags or trays using form-fill-seal equipment. For pillow bags, film is pulled from rolls, formed into a tube, filled with product, and sealed at the top and bottom by heated jaws. For tray packs, plastic trays are filled and lidded with sealed film using MAP systems, replacing ambient air with nitrogen and carbon dioxide. Each pack is labeled with product ID, batch number, and expiration using inkjet printers or label applicators. Vision systems confirm label placement and code legibility. Weighed packs are verified for target range and conveyed to check weighers. Under or overweight packs are removed via pneumatic rejectors. Packaged units are collated and loaded into cartons. Carton erectors fold and glue cases, while robotic arms load a fixed number of bags or trays per box. Cartons are sealed, labeled, and scanned for tracking codes. Logistics data is applied using print and apply labelers that communicate with the plant's ERP system. Boxes are transferred to robotic or gantry-style palletizers. These systems stack cases on wooden or plastic pallets in staggered patterns to optimize height and weight distribution. Pallets are stretch-wrapped using rotary arm or turntable wrappers. Finished pallets are tagged with shipment barcodes and stored in cold storage warehouses maintained at 20 degrees Celsius. All processing stages are monitored by a PLC integrated SCADA system. Control points include marination pump flow, batter viscosity, breading density, fryer oil temperature, freezer airspeed, and packaging line synchronization. Recipe management software ensures every batch conforms to target formulation and processing times. Sensor data is collected from load cells, thermocouples, optical sensors, belt encoders, and pressure gauges. Line operators access live performance dashboards from HMIs to monitor throughput, reject rates, and downtime per station. Alarms and parameter deviations are logged in the plant MES. Quality assurance involves sample testing at key stages. Strip dimensions are measured post-cutting with digital calipers. Batter pickup percentage is calculated by weight differential before and after coating. Oil content is checked using Soxhlet extraction post-fry. Internal temperature is verified post-freeze using calibrated thermometers. Microbial samples are taken from finished product and contact surfaces. Swabs are tested for total plate count, Listeria SPPER, and Salmonella SPP. Moisture, protein, and fat levels are confirmed via NIR spectroscopy or gravimetric methods. Product consistency is tracked against batch specifications. Yield data is compiled for raw input versus packaged output to monitor efficiency. Trimming loss, batter loss, breading recycle rates, and oil usage per kilogram of product are calculated for cost optimization. Rework loops return trimmings and off-spec strips to reprocessing lanes if permitted. In the high output production of Coca-Cola, the process is defined by continuous motion, absolute precision, and the seamless choreography of ingredients, machines, and packaging systems that transform individual raw components into millions of finished beverages every single day. The process begins deep within the mixing facility, where highly purified water, stripped of all minerals, chemicals, and organic material through a series of activated carbon filters, deionization beds, and ultraviolet treatment chambers, forms the foundation of the beverage. This purified water, tested continuously for pH, conductivity, and microbial presence, is stored in stainless steel tanks where it awaits dosing. Simultaneously, concentrated syrup, pre-mixed to exact proportions in controlled rooms, is pumped from insulated holding tanks through jacketed pipelines that maintain a constant temperature to prevent any crystallization or viscosity shifts. These lines carry the syrup to the blending system, where the water and concentrate meet inside high-speed mixing chambers fitted with vortex turbines that spin at thousands of revolutions per minute. These turbines ensure that every drop of syrup disperses evenly throughout the water stream, achieving uniform flavor concentration at massive scale. Inline refractometers measure sugar content and density in real time, adjusting flow valves to keep the bricks level within fractions of a percent of specification. Once blended, the now recognizable but uncarbonated Coca-Cola base enters a chilling loop, where it is passed through plate heat exchangers that rapidly drop the temperature to just above freezing. This cooling is critical because carbonation requires both precision and cold liquid. Warmer temperatures reduce the solubility of carbon dioxide, and the beverage must be stabilized before the gas is introduced. The chilled liquid is then sent to the carbonation unit, a sealed pressurized chamber where CO2 is injected under precise pressure and temperature control. The carbon dioxide gas, stored in liquid form in cryogenic tanks, is vaporized and filtered before injection, ensuring purity and taste neutrality. As the CO2 is forced into the beverage under pressure, it dissolves instantly, and the resulting mixture, now fully carbonated Coca-Cola, is routed into buffer tanks, where it is gently agitated to maintain consistency and avoid foaming. These tanks are under positive pressure to prevent degassing, and every line is monitored for CO2 saturation, temperature drift, and fill levels. From these tanks, the carbonated beverage moves directly to the filling lines, which operate with unbroken efficiency, handling thousands of bottles or cans per hour with mechanical repetition and minimal tolerance for variation. For bottles, the first step begins with preforms, small plastic tubes made of PET, fed from hoppers into a rotary oven where they are heated to a malleable state, then transferred into a blow molding carousel. Inside this machine, each preform is stretched and inflated with high-pressure air into the shape of a bottle inside precision-machined metal molds. The formed bottles are immediately cooled, trimmed, and transferred onto conveyors that carry them upright toward the filling line. Throughout this path, they remain untouched by hands and isolated from ambient air by enclosed systems that maintain sanitary conditions. As they approach the filler, the bottles are inverted and rinsed internally with sterile air or ionized water to remove any particles. They then pass under the filling heads, nozzles that lower into the neck of each bottle, creating a tight seal and filling them under counter-pressure conditions to prevent foaming or CO2 loss. The entire filling cycle for each bottle takes only a few seconds, monitored by laser-level sensors that detect exact volume. As each bottle fills, the flow is throttled to avoid turbulence, and the gas pressure is equalized to maintain carbonation stability. Immediately after filling, the bottles are transferred to the capping station, where precision-guided turrets place caps onto each one and tighten them with calibrated torque drivers. The caps themselves are fed from vibratory bowls that align them correctly and move them through high-speed chutes. As each bottle is capped, it is passed through a vacuum checker that detects seal integrity by measuring internal pressure, and any container that doesn't meet the threshold is automatically diverted from the line. In parallel to bottle filling, can production follows a similarly synchronized path. Aluminum cans arrive already formed, stacked, and nested, and are depalletized in towers that feed them one by one onto high-speed conveyor belts. These cans move through a rinse tunnel where jets of deionized water clean the interiors. Then dry blowers remove every drop before they reach the filler. Because cans can't be sealed under counter-pressure like bottles, they are filled with a slightly different method. First purged with carbon dioxide to displace oxygen, then rapidly filled with cold, carbonated Coca-Cola, and finally topped with lids while still under pressurized gas. The lid seamer seals each can by curling the edge of the aluminum lid around the lip of the can body and compressing it tightly with a roller under immense force. The seam is inspected by cameras and load sensors, and every few hundred units, samples are removed automatically and sent to inline X-ray or cutaway analysis to ensure structural integrity. Once sealed, the cans are dried again, passed through a date coder that prints production codes and batch identifiers directly onto the lid, and then sorted into lanes based on packaging format: single, multi-pack, or bulk tray. Now fully sealed, bottles and cans alike move toward labeling and secondary packaging. Bottles pass through shrink sleeve or wraparound labelers that align each container using optical sensors before a printed film sleeve is applied and shrunk into place using steam or infrared tunnels. Can multi-packs are grouped into clusters by mechanical pusher arms and wrapped in printed film or placed into cardboard carriers. Robotic arms lift and arrange finished units into cartons or trays, depending on regional packaging standards, and automated check weighers confirm product count and configuration within each package. After secondary packaging, the products move to palletizing stations. Here, robotic stackers use vacuum grippers or clamp heads to build pallets layer by layer, rotating and interlocking packs to maintain balance and optimize density. Slip sheets or corner boards may be inserted for additional stability. Once complete, each pallet enters a rotary stretch wrapper, where clear plastic film is wrapped under tension around the stack, binding it tightly to protect against vibration or shifting during transport. A thermal label is printed and applied to the outer film, displaying destination, pallet ID, and manufacturing metadata. Every part of the line, from syrup mixing to final wrapping, is connected to a centralized control system, often SCADA-based, which aggregates data from thousands of sensors across the production floor. It tracks real-time flow rates, fill volumes, pressure changes, CO2 consumption, label placement accuracy, packaging efficiency, and quality checkpoints. Alerts are triggered the moment a parameter deviates from its programmed limits, prompting either automatic correction by servo-driven actuators or shutdown protocols to isolate the issue for inspection. Quality assurance is deeply embedded into the process. Sample bottles and cans are pulled at regular intervals by robotic pickers and sent to adjacent quality labs, where automated instruments test for brix levels, carbonation volume, pH, color density, and turbidity. Gas chromatographs may analyze flavor profile consistency, and oxygen analyzers confirm shelf life integrity. Retention samples are archived from each production batch in cold storage, enabling full traceability in case of future inquiry. Cleaning in place systems activate between flavor runs or at set intervals, flushing pipes, tanks, and filling valves with heated caustic solutions, followed by acid rinses, and finally with purified water. All internal product contact surfaces are sanitized, and the data logs are updated with each wash cycle. This ensures the system is sterile before the next production batch begins, whether it's more Coca-Cola or a different product line altogether. All along the line, mechanical timing is critical. Bottles that arrive milliseconds too soon or too late can cause backup or collision, so every machine is programmed to respond to product flow, spacing, and acceleration. Timing screws, sensors, and motorized star wheels maintain precise positioning, and buffer conveyors absorb temporary surges without stopping the line. Overhead, cameras and inline vision systems inspect every package for branding alignment, color accuracy, seal integrity, and tamper evidence, discarding any product that fails visual QA. From a distance, the system appears to operate like a single, unified machine: syrup, water, gas, packaging, and automation all working as one organism, never pausing, never deviating. Every bottle and every can moves through this stream of equipment with exacting control, shaped not by hand, but by air pressure, centrifugal force, liquid dynamics, and heat energy, and by the software that orchestrates it all behind the scenes. The production of cherry Coca-Cola begins with the coordinated movement of ingredients through a tightly integrated system of tanks, pipes, mixers, fillers, and control panels, where every second of the process is timed, and every variation in flow, pressure, or temperature is monitored and corrected in real time. The defining element of this beverage, the distinct cherry-flavored profile, requires its own set of ingredients to be introduced at specific intervals within a continuous fluid stream, and the entire operation is driven by automation that ensures each bottle or can delivers the same flavor, carbonation, and experience without deviation. At the heart of the operation lies the mixing zone, a sealed chambered area of the factory where the formulation begins not with bottles or packaging, but with the controlled blending of ultra-purified water and concentrated syrup. The water itself is subjected to a multi-stage filtration process that removes every mineral and contaminant through reverse osmosis membranes, UV sterilization lights, activated carbon beds, and deionization columns. The final water output is chemically neutral, consistent in temperature, and free of flavor interference, ensuring it will not alter or dull the delicate cherry infusion that characterizes the product. Simultaneously, the cherry Coca-Cola-based syrup is prepared in mixing tanks where measured amounts of sweeteners, flavor agents, acidity regulators, and natural cherry extracts are combined into a thick, dark syrup with precise viscosity. Each batch is homogenized with high-speed impellers, continuously monitored for density using inline refractometers, and sampled through sterile taps for real-time verification of its sugar content, aroma, and visual clarity. Once verified, the syrup is stored in insulated holding tanks fitted with agitators to prevent settling and ensure uniformity prior to dosing. When the purified water and cherry-infused syrup are combined, they are fed into high-shear blending, chambers where specially engineered turbines swirl the mixture at controlled speeds to ensure total integration. These blending units include flow regulators that adjust the syrup-to-water ratio down to 0.1% so that every liter leaving the chamber maintains exact sweetness and acidity levels. This blending is continuous and uninterrupted, forming a central stream of cherry Coca-Cola base that is directed toward the chilling loop. Before carbonation, the mixture is rapidly cooled using a set of plate heat exchangers where cold glycol fluid moves through alternating stainless steel plates, drawing heat from the beverage as it flows in an adjacent channel. The cooling process is essential, dropping the beverage temperature to near freezing, around 0 to 2 degrees Celsius, which allows the carbon dioxide to be absorbed efficiently and held within the liquid under pressure. Once chilled, the drink enters a sealed carbonation unit. Inside this pressurized chamber, carbon dioxide gas, stored in liquid form at cryogenic temperatures, is vaporized, filtered, and then injected into the cold cherry Coca-Cola base through a sparging system that disperses the gas evenly throughout the liquid. The CO2 dissolves into the beverage instantly due to the low temperature and high pressure, and the resulting carbonated drink flows forward to the buffer tanks, where it is gently mixed and held under pressure to prevent gas release or foaming. These buffer tanks act as holding silos between mixing and filling, maintaining consistent temperature and carbonation levels while regulating the supply to each individual filling line. The tanks are fitted with pressure sensors, degassing valves, and agitation paddles that rotate at slow speeds to preserve homogeneity without disturbing the carbonation level. From here, the carbonated cherry Coca-Cola is ready to be dispensed into containers at high speed. If bottles are the intended format, production begins with PET preforms, small test tube-shaped plastics that are loaded into feed trays and passed through a rotating oven chamber fitted with infrared heaters. The preforms are warmed to a pliable temperature before being inserted into steel molds, where compressed air blows each preform into the shape of a bottle within milliseconds. The molds are cooled, and the newly formed bottles are ejected onto conveyor lanes, where they begin their journey to the filling line. Each bottle passes through an inversion unit, where they are turned upside down and rinsed with filtered air or ionized water to eliminate static charge and remove any residual particles. Once cleaned, they are flipped back upright and enter the filling carousel, a large rotating ring with multiple filling heads. As each bottle passes underneath a head, it is sealed airtight and filled using counter-pressure filling. CO2 is first used to purge oxygen from the bottle. Then the beverage is dispensed, equalizing pressure to avoid foaming or gas loss. As the bottle fills, a level sensor determines the precise volume. and flow is shut off with a clean break once the target fill is reached. The next stage is capping. Cap hoppers sort and orient the plastic caps, feeding them down a chute where robotic arms place each cap onto the filled bottle. A torque-controlled spindle tightens every cap to an exact specification, and a vacuum sensor checks that each seal is secure. Each bottle then passes through a high-speed date printer that applies production information, including line number, time code, and expiration date. Can filling follows a similar track, but on a separate line with specialized machinery. Empty aluminum cans arrive pre-formed, palletized, and stacked in tall columns. These stacks are depalletized and fed into the can rinsing tunnel, where they are cleaned with a high-pressure deionized water spray, then dried using high-speed air knives. Cleaned cans are conveyed directly into the filling system, where they pass beneath a gas flush station that replaces internal air with carbon dioxide to maintain freshness. As the cherry Coca-Cola is dispensed into each can, the filling head retracts, and a lid is placed onto the top of the filled can by a precision seamer. This machine uses a dual-action compression and curl technique to lock the lid onto the can body, creating a hermetic seal. Immediately afterward, the can is cleaned again externally, printed with production codes, and passed to the packaging lanes. At this point, both bottles and cans converge into the secondary packaging area, where products are grouped, aligned, and prepared for shipment. Bottles are collected into multi-packs using servo-controlled arms that lift and guide them into shrink film, which is wrapped and sealed around the group before passing through a heat tunnel that shrinks the film tight. Cans are guided into multi-lane collators that align sets of 6, 12, or 24, depending on the package, and apply either shrink wrap or cardboard wraps printed with branding and barcodes. Cameras verify each pack's alignment, color fidelity, and integrity before they are cleared for stacking. Packaged units move toward robotic palletizing systems, where vacuum lifters and grip arms organize them into stable layers, rotating the orientation of each pack to create interlocking rows. Slip sheets are inserted between layers, and once the pallet reaches full height, it is transferred into an automatic stretch wrapper, which encases the pallet with tensioned film from top to bottom. A printed label with barcodes, destination data, and production batch is applied to the outside, and the pallet is transferred to the loading dock for transport. Meanwhile, every single movement on the production floor is tracked by an integrated control system, a network of programmable logic controllers and interface stations that monitor temperature, pressure, syrup ratios, carbonation levels, fill rates, and flow speed. The system adjusts each parameter in real time. If syrup density increases due to ambient temperature, pumps slow fractionally. If bottle alignment drifts off center, the guide rails shift laterally. If carbonation drops even slightly, the gas injector valve pulses at higher frequency until the correct level is restored. Throughout the process, quality assurance teams collect real-time data from sensors and pull physical samples at intervals. These samples are sent to inline labs, where technicians run automated tests using densitometers, CO2 analyzers, pH probes, and colorimeters to ensure each bottle or can meets flavor, appearance, and stability specifications. A taste panel may confirm final flavor consistency before the batch is cleared for release, and a retention sample is archived for traceability. Between batches, the entire system undergoes a clean-in-place CIP procedure. Pipes, valves, tanks, and filling heads are flushed with heated alkaline solutions, followed by acidic rinses and sterilization stages. Sensors monitor residue levels in rinse water, and the system will not allow a new batch to begin until cleanliness thresholds are met across the entire line. Inside the production facility dedicated to Coca-Cola Zero, the operation begins with a steady rhythm of systems calibrated to blend, chill, carbonate, and package a product that relies on absolute precision. Because unlike its sugar-sweetened counterparts, Coca-Cola Zero is formulated with no sugar at all, relying instead on an exact balance of non-nutritive sweeteners that must be handled with extraordinary control to maintain both flavor integrity and regulatory compliance. The process begins not with packaging, not even with carbonation, but with water. Water that has been stripped of every mineral, ion, and microbe through a comprehensive purification chain that includes activated carbon filtration, multi-stage reverse osmosis membranes, ultraviolet sterilization, and final stage polishing filters to ensure that every molecule entering the blend tanks is completely neutral. This water, once purified, is cooled immediately and transferred into a network of stainless steel supply tanks, each one connected to high-flow dosing manifolds, where the Coca-Cola Zero concentrate is introduced. Unlike other formulas, the Coca-Cola Zero syrup contains highly sensitive ingredients that must be mixed with close control over both flow rate and agitation speed. A series of variable speed turbines inside a baffled blending chamber begins to stir, drawing in sweetener concentrates from microdosing pumps which meter out fractions of grams per second, ensuring that every liter of finished product will contain only the approved quantity of aspartame, acesulfame potassium, and other formulation components. The syrup is mixed with chilled, purified water in a continuous loop, constantly circulating through inline density sensors and refractometers that verify every measurable characteristic of the mixture: its Brix equivalent, its acidity level, its color profile, and its consistency, all monitored by SCADA systems that relay performance data to centralized control stations positioned throughout the factory floor. If the syrup becomes too concentrated, water flow is increased fractionally. If any temperature drift is detected in the mixing tank, the coolant jacket is adjusted to compensate instantly. The goal is absolute uniformity. Every second, every drop must match the one before it. As the base liquid moves into the carbonation stage, it passes through a final chilling module where its temperature is brought down to a near freezing range. At this point, the beverage is ready for carbonation. The carbon dioxide gas, stored in its own cryogenically cooled system, is injected into the mixture using a high-efficiency carbonator, a pressurized steel chamber where the CO2 enters under regulated pressure through micro-diffusers, creating billions of microscopic bubbles that dissolve immediately into the cold liquid. The flow of CO2 is continuously calibrated according to beverage temperature, system pressure, and product viscosity, with flow sensors and back pressure valves maintaining stability as thousands of liters pass through each hour. Once fully carbonated, the beverage is routed into pressurized holding tanks, buffer vessels that serve as the final point of quality assurance before the product reaches the filler. These tanks are lined with level indicators, gas traps, and temperature probes, all synchronized to maintain the carbonation level while gently agitating the liquid to prevent stratification or foaming. Here, any final testing is performed in line. Carbonation volume, turbidity, residual sweetness, and pH are verified one last time. A sampling valve allows automated collection of product every few minutes, and that sample is passed directly into a micro lab for flavor standardization analysis using spectrophotometry and gas chromatography. Meanwhile, the packaging line is already in motion. For plastic bottles, the process starts with injection molded preforms, small and thick-walled, which are delivered in bulk and stored in hoppers above the blow molding machines. These preforms descend through a heater array where infrared panels warm them to a precise forming temperature before they are dropped into two-part molds. Compressed air is blasted inside, expanding the plastic against the inner mold walls to create full-size bottles instantly. As the mold opens, cooled air is used to solidify the bottle's shape, and a robotic gripper places each new bottle upright onto a moving conveyor that feeds directly toward the filling station. Before any liquid enters the bottles, they are passed through an inverted rinsing tunnel where ionized air is sprayed inside each one to remove microscopic particles. They continue along the line toward the filler, where a rotary system spins each bottle into place beneath a filling valve. This valve descends into the mouth of the bottle, creates a pressurized seal, and initiates a filling sequence that begins with a brief CO2 purge to eliminate oxygen and preserve shelf stability. The pressurized beverage flows into each bottle in just under 2 seconds, with real-time fill level sensors using laser measurement to verify that each container is consistent to the milliliter. There is no overflow, no foam rise, no turbulence. The pressure balancers are engineered to make the fill seamless and silent. Once filled, the bottles pass immediately to the capping turret. High-speed feeders deliver bottle caps from a bowl sorter into the capping head, which presses each cap onto the threads and twists them into place using torque-monitored spindles. Each cap is verified for application tightness and angle, and a vacuum test is performed at random intervals by an inline tester that verifies the seal by measuring pressure drop inside a chamber. If a cap is misapplied, the bottle is instantly diverted from the line. After capping, the bottles pass through a date and batch printer, which uses thermal inkjet or laser etching to apply identification directly to the neck or shoulder of the bottle, depending on line configuration. In parallel, aluminum cans are prepared on their own dedicated track. Delivered by the pallet, preformed cans are depalletized and sent through a high-speed depuck system that guides them into the line one at a time. Each can passes under a rinse sprayer and then through a drying tunnel before entering the can filler. This equipment is built for volume. Multiple nozzles dispense product simultaneously, filling dozens of cans per second, each one pressurized beforehand to prevent foaming during the rapid fill. A lid is placed on each can immediately after filling, and a seam roller presses the lid onto the body, creating a hermetic seal that is pressure tested, scanned by vision systems, and validated against a standard profile. Cans are printed with batch codes and transferred to the packaging section. Now, both bottles and cans proceed to the secondary packaging area, where multi-packs are created using automated grouping systems. Bottles are collated into clusters of 6, 12, or 24, wrapped tightly in shrink film, and sent through a steam tunnel that shrinks the plastic smoothly around the group without obscuring the labels. Cans are similarly grouped and placed into printed cardboard sleeves or plastic rings, depending on the destination. Each group is weighed, scanned, and inspected for alignment before being transferred into cartons. Carton erectors form boxes from flat stock, fold them automatically, and glue them using hot melt adhesives before they are filled with packs by robotic arms that stack them precisely inside. Once loaded, the cartons are sealed, labeled, and conveyed to a palletizing system where mechanical arms stack them onto pallets in programmed patterns to maximize space and stability. A slip sheet may be inserted between layers, and once the stack is complete, it moves into a stretch wrapper that encases the pallet with plastic film to lock it tight for shipping. The entire pallet is weighed, labeled, and scanned before being queued for loading. Spaghetti production in factories begins with the precise blending of durum wheat, semolina, and water in massive stainless steel mixers that rotate at controlled speeds to ensure uniform hydration. The semolina used is specially milled to have a coarse texture that provides the ideal structure for pasta, unlike finer flours used in bread or cakes. Water is added in exact ratios, typically around 30 to 33% by weight, to activate the gluten without making the dough too sticky or too dry. The mixing process takes approximately 15 to 20 minutes, during which sensors monitor temperature and moisture levels to prevent overheating or uneven consistency. Once the dough reaches the right consistency, it is fed into a vacuum deaerator that removes trapped air bubbles, preventing imperfections during extrusion. This vacuum step is critical because air pockets can cause the spaghetti to break or cook unevenly later in the process. The dough then enters a twin screw extruder, where hydraulic pressure forces it through bronze or Teflon dies with hundreds of tiny holes arranged in precise circular patterns. Bronze dies are preferred for traditional pasta because they create a slightly rough surface that holds sauce better, even though they wear down faster than Teflon. Each die is engineered to produce strands exactly 2 millimeters in diameter, with tolerances of less than 0.05 millimeters to maintain consistency across entire production runs. As the dough is extruded, it emerges as continuous strands that are immediately cut into standardized lengths of 25 to 30 centimeters using high-speed rotating blades. The cut strands are gently guided onto moving conveyor belts made of food-grade polymer that prevent sticking while allowing airflow underneath. These belts carry the spaghetti into the first drying chamber, where temperature is held at 35 degrees Celsius, and humidity is kept below 60% to begin slow moisture removal. Drying is not a single-step process. It occurs over 4 to 6 hours across multiple zones, with gradually decreasing humidity and increasing temperature. In the initial drying zone, moisture is slowly drawn from the outer surface of the strands to prevent cracking or surface hardening. The second zone raises the temperature to 45 degrees Celsius while reducing relative humidity to 40%, allowing moisture to migrate from the core outward. In the third zone, the temperature climbs to 55 degrees Celsius and humidity drops to 30%, accelerating the drying of the pasta's interior without collapsing its structure. A final conditioning zone at 30 degrees Celsius and 55% humidity allows the pasta to equilibrate, ensuring even moisture distribution throughout each strand. Throughout the entire drying process, robotic arms with infrared sensors continuously scan each batch for cracks, warping, or discoloration, automatically diverting defective strands. After drying, the spaghetti is cooled in a controlled environment to room temperature over the course of 90 minutes to prevent condensation and microbial growth. Cooling is done with filtered, dehumidified air to avoid reintroducing moisture that could lead to spoilage during packaging. Once cooled, the strands are gently shaken and separated by vibrating screens that disentangle any strands that may have adhered during drying. A powerful air stream then blows away any residual semolina dust or small fragments that could affect texture or shelf life. The spaghetti is then fed into precision weighing systems that portion out exact quantities, typically 500 grams or 1 pound, into food-grade polypropylene bags. Each bag is sealed with heat, creating an airtight barrier that protects against oxygen, moisture, and pests for up to 2 years. Inside the sealed bag, a small oxygen absorber packet is often included to further extend shelf life by eliminating residual oxygen. Before sealing, a metal detector scans each package to ensure no foreign materials, such as metal fragments from machinery, have contaminated the product. The packaged spaghetti is then labeled with batch numbers, expiration dates, and nutritional information using high-resolution inkjet printers that operate at speeds exceeding 100 packages per minute. Each label is scanned and logged into a centralized digital tracking system that links every box to its exact production time, raw material source, and quality control checkpoints. The boxes are stacked by robotic arms onto pallets, wrapped in stretch film, and moved via automated guided vehicles to a climate-controlled warehouse. The warehouse maintains a constant temperature of 18 degrees Celsius and humidity below 50% to preserve the pasta's texture and prevent mold. Before shipment, random samples are pulled from each batch and sent to an on-site laboratory for microbiological testing, including checks for Salmonella, E. coli, and mold spores. The lab also performs texture analysis using a texture analyzer that measures the firmness of cooked spaghetti to ensure it meets the industry standard al dente criteria. Each batch is tested for cooking time, with the target being 8 to 10 minutes in boiling water, and deviations trigger an automatic review of the drying parameters. Once cleared, pallets are loaded onto refrigerated trucks that maintain a steady 10 to 15 degrees Celsius during transit to prevent thermal degradation. The entire production line operates 24 hours a day, 7 days a week, with only brief scheduled maintenance windows to clean and inspect critical components. Every hour, the extruder dies are manually inspected and cleaned with high-pressure steam to prevent bacterial buildup in the microscopic holes. The mixing tanks are sanitized with food-grade citric acid solutions after every batch to eliminate cross-contamination risks between different pasta shapes. Workers in the facility wear full hairnets, gloves, and shoe covers, and all entry points have air showers that blow away dust and particles before entry. The factory's HVAC system filters air 15 times per hour, maintaining a Class 8 clean room environment to meet international food safety standards. All equipment is designed with smooth, seamless surfaces and no crevices where dough or debris could accumulate and become a breeding ground for microbes. Robotic vision systems monitor the color and shape of every strand exiting the extruder, rejecting any that deviate from the established visual profile. If a strand is found to be too thick, too thin, or irregularly shaped, the system automatically adjusts the extrusion pressure in real time to correct the issue. The factory produces over 12 million kilograms of spaghetti annually, enough to feed approximately 200 million servings per year. Each kilogram of finished spaghetti requires precisely 1.1 kilograms of semolina, with the remaining 0.1 kilogram lost to moisture evaporation during drying. The water used in production is filtered through reverse osmosis systems to remove minerals that could affect dough texture or flavor. Wastewater from cleaning is treated in an on-site biological filtration plant before being safely discharged into municipal systems. Used semolina dust is collected and sold to livestock feed manufacturers, reducing waste and contributing to a circular economy model. The energy used in drying is partially recovered through heat exchangers that capture exhaust heat and reuse it to preheat incoming air. The factory's lighting system uses motion-activated LED panels that dim or turn off in unoccupied zones to reduce electricity consumption. Every machine on the line is connected to a central AI monitoring system that predicts maintenance needs based on vibration patterns and motor load. This predictive maintenance reduces unplanned downtime by over 40% compared to traditional scheduled servicing. The factory's quality control team includes food scientists with PhDs who regularly test new semolina varieties and drying algorithms to improve efficiency. New production runs are always preceded by a trial batch that undergoes sensory evaluation by trained tasters who assess texture, aroma, and mouthfeel. Each factory worker undergoes quarterly food safety certification and participates in simulated contamination drills to maintain readiness. The entire process, from raw semolina to sealed box, takes less than 7 hours from start to finish, making it one of the most efficient food manufacturing systems in the world. No preservatives are added to the spaghetti, relying entirely on low moisture content and airtight packaging for long-term stability. The final product contains no cholesterol, no saturated fat, and no added sugar, making it a nutritionally neutral staple in global diets. Every strand of spaghetti produced in this facility is identical in diameter, length, density, and cooking behavior to the one before it, thanks to relentless automation and real-time feedback systems. The factory operates with zero tolerance for human error in the final packaging stage, as even a single mislabeled box could trigger a nationwide recall. Lasagna production in factories starts with a dense, coarse semolina flour blended with chilled, purified water in a slow-turning horizontal mixer that prevents overdevelopment of gluten. Unlike spaghetti dough, lasagna dough is formulated to be slightly drier and more rigid, enabling it to hold its shape during stacking and baking without becoming soggy. The water used is pre-cooled to 12 degrees Celsius to maintain dough temperature below 24 degrees during mixing, preserving the natural starch gelatinization profile. After blending, the dough is rested for 15 minutes in a sealed, humidity-controlled chamber to allow gluten strands to relax and absorb moisture evenly. This resting phase is critical. It reduces the risk of sheet cracking during the subsequent rolling process by allowing internal tension to dissipate. The dough is then fed into a tandem roller system composed of hardened steel cylinders that compress the dough in 7 incremental passes, each reducing thickness by only 0.08 millimeters. The final roller gap is set to 0.62 millimeters, producing sheets so uniform that laser sensors can detect deviations as small as 0.01 millimeters across the entire width. As the sheets emerge, they are immediately swept by a gentle stream of dry, filtered air to prevent adhesion to the metal conveyors and to initiate surface drying. The sheets are not cut immediately. Instead, they travel continuously along a 30-meter long drying track suspended above a series of radiant infrared heaters. These heaters emit targeted wavelengths that dry the top and bottom surfaces at different rates, minimizing curling and warping caused by uneven moisture loss. Humidity sensors embedded in the drying tunnel adjust airflow in real time, maintaining a gradient that pulls moisture from the core outward without forming a hard outer shell. Every 12 seconds, a robotic arm lifts a section of the continuous sheet and tests its tensile strength by gently stretching it between calibrated claws. If the sheet fractures or elongates beyond 12% of its original length, the system flags the batch and adjusts the next dough batch's hydration level automatically. Once dried to a moisture content of under 10%, the sheets are cooled in a tunnel filled with recirculated, sterile air to prevent reabsorption of ambient moisture. At this stage, the lasagna sheets are still flexible enough to be handled without breaking, but too brittle to be rolled back into dough. A high-speed cutting station then slices the continuous ribbon into individual rectangles using tungsten carbide blades that operate at 1,200 cuts per minute with zero blade wear. Each piece is precisely 10.2 centimeters wide and 15.5 centimeters long, sized to fit standard commercial lasagna pans and retail packaging dimensions. After cutting, the pieces are lifted by electrostatic air knives that use controlled static charges to separate and align them without physical contact. They are then conveyed over a vibrating platform that gently shakes off residual semolina dust, which is collected and recycled into animal feed. The sheets pass through an ultraviolet sterilization chamber that eliminates surface microbes without altering taste, texture, or nutritional value. Each sheet is individually inspected by a machine vision system that scans for color consistency, surface texture, and the presence of any embedded foreign particles. Defective pieces are ejected into a waste bin using compressed air jets, while acceptable sheets continue to the packaging line. Packaging occurs in a sterile environment where each lasagna sheet is placed into a pre-formed, food-grade cellulose tray lined with a moisture barrier film. The trays are sealed under vacuum with a heat seal lid that creates an airtight barrier, extending shelf life to 18 months without preservatives. Inside each sealed tray, a small silica gel packet is inserted to absorb any residual moisture that might develop during transit or storage. Before sealing, each tray is passed through an X-ray scanner that detects metallic contaminants, plastic fragments, or glass particles invisible to the naked eye. Every package is labeled with a unique QR code linked to its production batch, ingredient source, and quality assurance logs accessible via manufacturer portals. The sealed trays are stacked by robotic arms onto pallets wrapped in heat shrink film, then moved by autonomous guided vehicles to climate-controlled storage. Storage rooms maintain a constant 16 degrees Celsius and 45% relative humidity to prevent brittleness or microbial growth over extended periods. Random samples are pulled daily and sent to the in-house lab for cooking tests, where technicians measure rehydration time, firmness after boiling, and sauce absorption rate. The target is for each sheet to absorb exactly 45 milliliters of water in 8 minutes of boiling, achieving a texture that remains firm yet pliable under cheese and sauce. Lasagna sheets are never pre-cooked. Their dry state is intentional, allowing consumers to layer them directly into casseroles without blanching. The entire production line runs continuously, processing over 800,000 sheets per hour, with each machine synchronized to within 0.01 seconds of the next. Maintenance is performed during scheduled 15-minute windows every 4 hours, during which steam jets clean every surface the dough contacts. No lubricants are used on any part of the machinery that touches the dough. Instead, food-grade silicone coatings are applied to rollers to prevent sticking. All personnel entering the production area must pass through an airlock chamber that blows away particulates before entry, and gloves are changed every 30 minutes. The factory's ventilation system filters air 22 times per hour, maintaining a particulate count lower than that of a hospital operating room. Every batch of semolina is tested for protein content before use, with only flour yielding 12.5 to 13.2% gluten accepted for lasagna production. The water used is reverse osmosis, purified and mineral balanced to ensure consistent dough behavior across different regional water sources. Wastewater from cleaning is treated with activated carbon and UV sterilization before being reused for non-food contact purposes like floor washing. Unused semolina dust is sold to organic fertilizer producers, and packaging film scraps are recycled into industrial plastic pellets. Energy recovery systems capture heat from the drying tunnels and redirect it to pre-warm incoming water, reducing overall energy consumption by 37%. AI algorithms analyze vibration patterns in the rollers and predict bearing failures up to 72 hours in advance, eliminating unscheduled downtime. Each lasagna sheet is designed to expand by no more than 3% when cooked, ensuring layers remain flat and evenly distributed in the finished dish. No additives, preservatives, or enzymes are used. Only semolina, water, and time. The final product contains zero cholesterol, no trans fats, and less than 0.1% sodium, making it suitable for dietary restrictions worldwide. Each sheet is identical in weight, thickness, and cooking behavior to every other sheet produced in the last 10,000 batches. The factory produces enough lasagna sheets annually to assemble over 50 million individual lasagna dishes, each one ready to be layered, baked, and served. Once packaged, the trays are loaded onto refrigerated trailers that maintain a steady 8 to 12 degrees Celsius during transit across continents. Noodle production in factories begins with the careful selection of high-protein wheat flour, often blended with egg solids or alkaline salts, depending on the regional style being manufactured. Unlike pasta, many noodle varieties require the addition of kansui, a mineral solution of potassium and sodium carbonate, to achieve their characteristic yellow hue and springy texture. The flour and liquid ingredients are mixed in a vertical spiral mixer that gently folds the dough rather than kneading it aggressively, preserving delicate gluten networks. The mixing process lasts only 10 to 12 minutes, as prolonged agitation would overdevelop gluten and make the noodles too chewy or tough. Once combined, the dough is immediately transferred to a resting chamber where it sits under a weighted lid for 20 to 30 minutes, allowing hydration to complete and proteins to relax. This resting phase is non-negotiable. It enables the starch granules to swell fully, ensuring even cooking and preventing mushiness later in the process. After resting, the dough is passed through a series of precision rollers that flatten it into a continuous ribbon, each set reducing thickness by just 0.05 millimeters to avoid tearing. The final ribbon is typically 1.2 millimeters thick, but this varies slightly depending on whether the noodles are intended for ramen, udon, or instant cup varieties. As the ribbon exits the rollers, it is lightly dusted with rice flour or cornstarch to prevent sticking, avoiding wheat-based flours that could alter flavor or cooking behavior. The sheet then moves onto a perforated conveyor belt, suspended above a low-temperature drying zone that begins moisture removal without hardening the surface. In this initial stage, air at 28 degrees Celsius flows upward through the belt,